here. Okay.
Right. Yep.
So this is forward slide. Advances solar and solar dynamos. So we have today and tomorrow we have 6 oral sessions. Also we have poster sessions. So I'd like to draw attention to poster sessions, and the posters will be the whole day. So it's not like other meetings. I requested that posters are presented the whole day. The morning, afternoon, you can look during lunchtime. And poster presenters, please nearby of your posters. This morning that what I saw some posters, but nobody was near the posters. It's very important. And will be also poster 1-minute poster presentations for people who submitted this request. So it will be very brief at the end of this session. Will be very brief poster presentations. So let's start. Any questions? Okay, so let's start our first talk. So Hiroki Miyahara will tell about insights into the initiation process of ground minima suggested by the high precision carbon-14 analysis.
Thank you very much for having me here. Today, I'd like to talk about the possible process of the onset of the ground solar minimum reduced by the high precision analysis of carbon-14. We have been trying to improve the precision of carbon-14 analysis for the past 10 years, and we have now achieved like 4 times better precision than before. And today I'd like to introduce some of the results based on those measurements. So here is the sunspot data for the past 400 years, and it shows that the sun has long-term variations that sometimes cause the ground solar minimum. And if we want to know the variation further back in time, then we can use the proxy record, right? Carbon-14 in tree rings and barium-10 in ice cores. And these are the examples of the reconstructions for the past millennium. And they show that the sun has experienced some other minima, such as the Spira minimum here, Wolf minimum, and some small one in here, Old minimum. And it also shows that the sun has experienced some period where the sun kept a relatively high solar activity, like the medieval solar maximum. And what we want to know is to understand the process, how the ground minima occur. And for that, we are trying to retrieve the information of the 11-year solar cycles, because they might give some clues regarding the condition of the sun, including the meridional circulation. So here is the slide showing the basics of the carbon-14 and barium-10. Both are produced by the galactic cosmic rays that are moderated by the solar wind in the heliosphere. So we expected higher production rate when solar activity is weak and the solar magnetic field wind is weaker. And barium-10 would be stored in ice sheets through the precipitation of snow. And although they accompany some dating uncertainties, annual layers have been counted back to 60,000 years ago. On the other hand, carbon-14 would be stored in tree rings after circulating within carbon cycle that include the atmosphere, ocean, and biosphere. The problem of the carbon-14 is that the amplitude of the variation would be significantly reduced during the circulation, so we need a real high precision analysis. But the advantage is that the trees have visible annual layers, so we can achieve the precise annual resolution. And here is the system used for the measurement of carbon-14. This is the accelerator mass spectrometer. And the typical measurement precision of the accelerator mass spectrometer is about 0.2 to 0.3%, which are comparable to the variation of carbon-14 variation for the decadal scales. So this is not enough to retrieve the information for each cycle. So we needed to improve the precision. And so we improved the system and the analysis code and the measurement strategies. And we finally achieved about 0.05% in 2020. And here is the example of the outcomes of such high precision analysis. And it's a bit hard to see under the light, but about 20 years ago, we had obtained the carbon-14 data for the mountain minimum. And during that time, the uncertainties were much larger. So we were only able to determine the mean length of cycles during the mountain minimum, which was about 14 years. And now we have extended the data towards the onset period of the mountain minimum, which are shown by the pink circles. And based on this data, and using the carbon cycle model, we reconstructed the solar cycles just before the mountain minimum. I'm sorry forgot to include the citations for the sunspot data, but these are the observation of the sunspot data. So here is the onset of the mountain minimum. And what we had expected is to have one long cycle just before them, but instead we found that the cycles started to be lengthened 3 cycles before the onset of the mountain minimum. And the longest cycle we found is the 16 years, although this is the best fit of the data, so it might accompany some uncertainty of about 1 to 2 years. But I'd like to emphasize that this 16-year cycle has been also found just before the Spira minimum in the 15th century. So the Spira minimum is here, and it started around 1415. And although we are still trying to improve the data and extending them, so we haven't done the calculation based on the carbon cycle model, but you can see there are 2 peaks here, which correspond to the cycle minima. And you can see that the peaks are rather apart each other, and the approximate length is about 16 years. So 16-year cycle is the common feature for the onset period of the Maunder and the Spira minima. And on the contrary, if we measure the carbon-14 for the period that solar activity is high, we find shorter cycles. For example, this is the data for the early medieval solar activity maximum. And although the data was taken in 2008, so it accompanies large uncertainty, so we had to take the wavelet analysis of the data. But it shows that the cycles were approximately 9 years during the time, 2 years shorter than the modern period. So, so we observe longer cycles during and before the grand minima, and this is a simplified view of the solar dynamo system, but the sunspots are suggested to be related to the polar magnetic field from the previous cycles. And so if you want to change the polar magnetic field, there are several ways, but one way is to change the efficiency of the advection of the magnetic field to the polar region. For that, the configuration of the sunspots could contribute to change the efficiency. But the other way is to change the meridional circulation in the convection zone. So if we slow down the meridional circulation, it could enhance the diffusion of magnetic field to increase the dissipation of magnetic field. So you can reduce the amount of the polar magnetic field. So 16-year cycle just before the ground minimum suggests that the speed of the meridional circulation was slower, and that it could be playing an important role in changing the solar activity level. Now, I'd like to talk also about the issues related to the separation of the signals of the solar proton events and solar cycles in carbon-14. And as you know, the carbon-14 is generally produced by the galactic cosmic rays, but recent studies have indicated that the extreme solar flare that accompanies high energy protons can also increase the carbon-14. And here's the production rate of carbon-14 for the event found so far. The largest event was the one found in 775, and now two of similar scale have also discovered like 5,000 BCE, 7,000 BCE. And these large events can be easily detected and separated from the signals of solar cycles, but it becomes difficult for smaller events. And in fact, even though we expect higher event rate for the smaller events, the number of the events identified so far is still limited because of the difficulty in the detection. And so it means that the sum of the carbon-14 variation still contains the information on the solar proton events and disturbing the signature of the solar cycles. And I'm hoping that our high precision analysis would contribute to separating these two signals. And here is the example which we succeeded to separate these two signals. And we were trying to measure the carbon-14 during the Wolf minimum here, which started around 1285. And we found that there were 3 jumps in carbon-14, suggesting the occurrence of solar proton events. And by removing these 3 events, we were able to reconstruct the solar cycles around the time. And we successfully captured the transition of solar activity from the very high activity state to the quiet phase. And the total length of these 2 cycles were about 25 years. So it suggests that either or both of the cycles were longer than 11 years. Now, these 3 arrows indicate the timings of these proton events, and 2 of them had occurred at the solar maximum, and 1 occurred at the declining phase, and which is consistent with the characteristics of the solar flare during the modern period. Now, this is our latest work, which is on the medieval solar activity maximum around here. Although the length of the data are still very short, we were able to detect one solar proton event in 1201 CE. And after removing this impact, we reconstructed the solar cycles around the time. And you can see that the length of the cycles were rather short around here. And it was approximately 7 to 8 years during the time. So again, it suggests the importance of the meridional circulation in regulating the solar activity level. Now, this slide is just to show the comparison of these proton events to the sunspots and red aurora record remained in the literatures. And we found that one red aurora event recorded in Chinese literature is showing a good match with the timing with this proton event. So they might be related to each other. So here is the summary. Our high precision analysis have allowed us to deepen our knowledge about the variation of 11-year cycles, and they consistently show that the cycle length tend to be longer during and before the solar activity weakening. So the meridional circulation could be very important for regulating the solar activity. Although, we have to now think about how we can change this one. And I'm hoping to discuss during this session. Thank you.
Well, thank you very much. Do we have questions online? Okay, so let's start, Irina.
Thank you very much for really, really interesting talk.
Thank you.
My question is about uncertainties and uncertainties of your measurements, and you discuss about level of point or
yes.
something. I forgot, sorry. But is it possible for you to convert it to uncertainties in sunspot number, for instance, or something what we know? But thank you.
Yeah, so I didn't have time to explain about the method, but uncertainties for length or amplitude, it's a bit different. But what we do is to make the possible synthetic curves for sunspot cycles and put them into the carbon cycle model and compare it with the measurement data. And so the amplitude has large uncertainty, I must say. But the length, in this paper, I forgot to include the uncertainty. But for example, here, the length now, we have uncertainty of about 1 to 2 years. So good enough for the comparison with the sunspot data. But for amplitude, I must say, it has larger uncertainty.
Thank you, Raka, for very nice talk. I have actually two small comments. One, you didn't mention, but probably you know that there was a full sunspot reconstruction for the last millennium based on Zurich radiocarbon measurements. We published in 2021, including sunspot and all cycles. My question is that you mentioned several times that the long solar cycle, 16 years, is a typical feature before a grand minimum. But for the Maunder minimum, it appeared 3 cycles before, not right immediately before. Then for Spörer, I think it was quite convincing. For Wolf, you had just some wavelet basis analysis. So how robust is the statement that right before the grand minimum, you expect an extended 16 years long cycle?
Yes, they both have 16 years. So the one you mentioned is the one shown here. The white one is the one based on the Zurich data. And what we found is that so the 16-year cycle happened 3 cycles before the Maunder minimum and just 1 cycle beforehand, Spörer minimum. But I didn't mention, but there are at least 2 cycles were longer before the Spörer minimum. It was the second one was like 14 years, although we have to make confirm this. So at least 2 cycles we need to have the grand minimum. That's the thing that we found. Although the transition of the lengths could be different by the event.
Okay.
Nice work, but so I have a concern about linking the time periods that you observe directly to the meridional circulation, because well, if the circulation slows down, there is another effect, which is that the cross-equatorial cancellation of the opposite bipoles, which are leading polarities, become more efficient, and you actually end up having stronger polar fields. Going from there to a minimum state is difficult. So this is, the results are nice. The interpretation from the dynamo perspective is a bit tricky.
Yeah, for that I need your help. But yeah, so it depends on the time scale of the magnetic turbulent diffusion. So it can result in both enhancement or reduction. And so yeah, I need to discuss with you about it. But the thing we found is just the slower meridional circulation beforehand. Thank you.
Okay, thank you. Some more questions? I have a question. You mentioned some flaring activity, some big flares.
Yes.
So is there any correlation between the cycles and flares? It's any correlation between length of the cycles or strength of cycles and flares?
I really want to work in the future because it happened during the transitional period from the high state to the quiet phase. So they might be related to each other, although which one is the first? The slower meridional circulation might affect the turbulence of the magnetic field, but also possible is that the large sunspots with complex configuration might have contributed to the reduction of polar magnetic field. So either is possible for now. So we want to know more about this. Thank you. Thank you.
Okay. Thank you.
A very nice work. You mentioned a correlation between the cycle length before maximum or minimum, right? Of Monte minimum type of. But did you find any correlation with the amplitude? It's possible to measure the amplitude of the cycles also. So what I mean is kind of a progressive decreasing in the amplitude of activity.
Yeah, that's also something that we try to retrieve, but for the moment, there are some assumptions for the reduction of the amplitude. So we haven't been able to, really discuss about it, but hoping to discuss about it in the future because we know here's the long cycle, but it doesn't seem to be much reduced. So the one thing that we need to take a few cycles to have a really low activity, but the transitions we need to work more. Thank you.
Okay, thank you very much again.
Thank you.
Okay, next talk is Dr. Nandi, precursors, predictions with observations of solar cycle 25. Where do we stand?
Well, good morning, and thanks to Sasha, Christoph, and the organizers for providing this opportunity. While this is coming up, I'm going to speak about solar cycle predictions. This is something that is very close to my heart, which also means there's scope for heartbreak. And you know the field, how checkered history it has been. I know that Christoph is following me, and we had a little bit of discussion to ensure that we don't have much of an overlap. So I'm going to focus on mostly the physics-based predictions of the solar cycle. And I want to give you a sense of what allows predictability, what breaks predictability, and how we've been doing over the past couple of decades. So this is just a context, and this is important because I think there is always a sense that anything that's like over 150 sunspot number is a very strong cycle. The average mean sunspot cycle, and Ilya would strongly agree with me there, is about 180. And if you look at the 1 sigma variation, it's like a 185 plus minus 40. So an average cycle is actually about 180. Anything below that is a moderate cycle. Anything over that gets to become stronger. So this is a sense that you should have. This is just a kind of average mean over the last 100 years. This is something that we want to try and predict the variation in the amplitude, and if possible, the period and the timing of the sunspot cycle as well. Well, so how have we been doing? This is the whole lot of predictions that was there for cycle 24. If you look at the spread of predictions for one cycle, this is the range encompasses the amplitude of all solar cycles that have ever been directly observed. It tells you the confusogram that it is. Does it change for cycle 25? This is cycle 25. And that itself tells you the story. But this is using a diversity of techniques. And I guess Christoph will be talking a little bit about this in a little while. Okay, so what is the context? So the context is that we would still like to be able to predict the solar cycle based on an understanding of the physics of the solar cycle. This is important. Failure is something that we should not be afraid of, because if we fail, we learn something. And this is really the motivation here, that we want to use physics-based models so that we can understand where we are failing and we can test the models. This sort of physics-based approaches to predictions have been to some extent successful in the terrestrial climate and weather community. But you have to remember that they have had a head start. It's been more than half a century that people have developed terrestrial models for climate and weather predictions. And it's only over the last couple of decades, in fact, cycle 24 was the first time that there were physics-based predictions. So this is a very new field that we're trying to figure out. Just a premise for the solar dynamo mechanism. So the toroidal component of the magnetic field gets produced in the interior. Let's not worry about where exactly. Usually the whole solar convection zone is involved in the process. And you see that on the right-hand meridional quadrant. And that production is due to the stretching of the poloidal component of the magnetic field of the sun, the dipolar component, by the differential rotation. When the toroidal flux tubes become strong enough, they can rise up due to magnetic buoyancy. During their rise, they're buffeted by helical turbulence, which can produce an alpha effect, the classic beam field alpha effect. When the active regions emerge on the solar surface, due to the Coriolis force, they have a systematic tilt, which produces a lot of statistical small bipole emergences. And from there, flux transport processes like turbulent diffusion, supergranular diffusivity, meridional circulation can create a large-scale dipole, which is known as the Babcock-Leighton mechanism, which operates well in the near surface layers, and you actually see the Babcock-Leighton process in operation, and it kind of completes the whole chain of activity. And that's how the dynamo goes. There are much more details, but I'm not going to go into the details of this now. Okay, there's one thing that is very important. Over the last decade or so, it's become very clear that the primary source of variability in the sun's polar field is the Babcock-Leighton mechanism, which is due to the emergence of systematically tilted bipolar emergence pairs. And you see that in the surface. This is based on observations. This is not theory. If you look at observed source function of the Babcock-Leighton mechanism, that has a direct correlation with the polar field that will build up. If you drive models based on the Babcock-Leighton mechanism, data-driven models, that has a very good match with the observed polar field that you see at the end of the minimum. So it's very clear, and let me reiterate that the Babcock-Leighton mechanism is the primary source of variability of the solar polar field. You cannot ignore observations. If you're still not convinced, sit down with me for lunch, and I'll show you observations. You cannot ignore them, right? Okay, well, so what are the sources of variability in this mechanism? When a flux tube is rising up from somewhere in the convection zone, they get buffeted by turbulence, and there is a scatter in the tilt angle, which produces a sort of a kind of like a scatter around the mean tilt angle that should follow from Joyce law. And that produces some sort of variability in the background source, which can then produce variability in the polar field. This is something that is observed. You can observe the scatter in the tilt angle. You can observe anomalously highly tilted active regions, and you can incorporate them in the models to see their impact on the polar field. And they match with the polar field that you're producing at the end of the cycle, right? That is also something that is very convincing. If you also look at the nonlinearities in the solar cycle, there is not just stochasticity, there's also a lot of nonlinearities. And they're not just related to the Lorentz feedback. There are multiple different mechanisms. I have just listed them here. I don't want to go into technical details. So you have a mechanism that is operating in the convection zone that has stochasticity because of the turbulence in the convection zone, noise in the convection. It has also got a lot of nonlinear processes that is involved in the dynamo mechanism. So it makes your life inherently difficult when you're trying to make predictions. And the first question that really arises in your mind is, can we really predict the solar cycle if you're dealing with a highly turbulent, highly nonlinear system? Well, so this is something that Paul generated quite some time back. This is kind of a nonlinear dynamic study of the solar cycle. If you increase the forcing, the dynamo number, make it a highly forced system, on the y-axis, you have the energy, which is like B square. You have regular solutions, which is singly periodic, and then you have bifurcation, which is a period doubling bifurcation, and eventually you get to completely irregular cycles, which means that you have loss of predictability at some point in time. So one open question is, where is the solar dynamo operating? Is it highly supercritical and nonlinear, which means it's on the extreme right, or is it just barely supercritical or subcritical, which means it's kind of operating in the regime which is somewhat more regular and predictable? Okay, so let's look at the dynamo equations. So if you break down the induction equation into its two components, the toroidal field component and the poloidal field component, there are the sources, there are the flux transport terms, and the diffusive terms. Many of these terms you can characterize as deterministic. These are the flux transport terms, which involve the transport of the magnetic field by the Maillard circulation. There is some feedback on this. There is feedback also of the magnetic fields and the differential rotation. But if you look at the torsional oscillation, that feedback is very small compared to the strength of the cycle itself. So you can more or less assume, and this is an assumption you would make in order to be able to progress towards making a prediction, that the flux transport terms are sort of deterministic, and there is no strong nonlinearity or stochasticity in those terms. You have the source terms, and that source term there, that's the precursor term, right? So you have the poloidal field sitting there, BP, and the toroidal field depends on the induction of that. That's fairly deterministic, and that's also proved from observations in the sense that there is a correlation between the polar field at minima and the sunspot cycle amplitude. Well, this term sitting there, the poloidal field source, is the one that introduces the stochasticity in the system, which breaks this chain of determinism and makes your life difficult in terms of prediction. The way out of there is that you can observe the net impact of all these processes as the polar field or the dipolar field at minimum. So if you can actually get there, which is the vector potential for the poloidal field, you can observe the R component of that on the solar surface. If your observations of the polar regions are good, and that's a question mark, then you have an escape route, in the sense you are taking the observations in and you're feeding that back into the equation, that's the observations, into the toroidal field evolution equation as the source, and then you solve for the toroidal field, which produces a sunspot cycle. So mathematically, the whole game of prediction, if you're doing a physics-based model, reduces down to observing the polar field, which is the vector potential is A here, at solar minima, and then running your simulations to predict the toroidal field that is for the upcoming cycle. This memory here, which is T0, is dependent on how long does it take for the flux transport processes to circulate the poloidal field to the generating layer of the toroidal field. It also sort of imbibes an essence of the stochastic power distribution in the system, in the sense that if your stochasticity is the time scale, let's say tau, then you start losing the memory in the system as, if you're over the stochastic perturbation timescale tau. So this memory in the system is actually very important in the sense of how long, how far in the future you can make predictions. Well, and so we have done dynamo simulations, which is stochastically perturbed, to look at the memory in the system. And what do you find? And whatever we do, so this is correlation between the polar field and the toroidal field of cycle n, n+1, n+2, n+3. The only correlation that survives eventually is the correlation between the polar field at the minimum of cycle n and the toroidal flux of cycle n+1. If you look at the observations, this is long-term polar faculae reconstruction by Andres. You see the same correlation there between the polar flux at the minimum of cycle n and the toroidal, the transport cycle amplitude of cycle n+1, and no correlation beyond that, implying that the memory in the cycle is one cycle. And you cannot really make very long-term predictions beyond one cycle. Well, so the theory of cycle predictability does agree with the observations. Well, the next question that you can ask is, can we extend this predictive window by trying and predicting the polar field itself? And that's where surface flux transport models step in, where what you do is you simulate by taking in inputs of active region emergence on the solar surface and putting in the supergranular diffusion, meridional circulation in the system. You build the large-scale polar field in the near surface layers and the poloidal component of the field. And then you can actually predict the polar field, and you can incorporate that in dynamo models also in a coupled way to make more long-term predictions and stretch the predictions maybe up to about 7-8 years. Right, and so this is what we did in 2018, where you see a result of a surface flux transport simulation. On the background, you have the polar faculae observations. The foreground is the thick lines, is the simulation results. And this is based on ensemble runs. You see that we are kind of done a reasonably good job in reproducing most of the cycles except the source for cycle 19. And again, I will not get into that, but that's a very difficult cycle to reproduce. And based on this, we coupled the surface flux transport model to a dynamo model and did the first century scale data-driven simulation of the dynamo, which does a reasonable job of reproducing past cycles. And based on this, we extended this model to make a prediction for cycle 25. Ours was the first prediction to indicate at the time when everybody was expecting a mono minima, remember 2017-18, that cycle 25 is going to be stronger than cycle 24, with a peak at 2024 with an uncertainty of about a year. All right, how is the polar field prediction doing? The thick green line is the polar field prediction. The background is the observation. It's done pretty well. However, a question mark is, are we comparing something not so accurate with an observation that is not so accurate because it's in the polar regions where the observations are highly projected, right? Okay, this is a synopsis of all the physics-based observations that has been done. That black horizontal line is cycle 24. You see the last two predictions there by Jiang, who's not here. And our prediction has a range which can go up to something like 150 in annual sunspot number. All right. So can we predict the solar cycle? We think yes. What is the best proxy for prediction? Is the poloidal field or the polar flux that is observed. How accurately can it predict is an open question mark. And this is something that is still in progress. How early can you predict? By using SFT and dynamo models, you can stretch this prediction up to, at best, 10 years before, but the predictive skill reduces as you go forward. And the outlook for cycle 25 is that it's going to be a weak to moderate cycle. I've listed down some challenges here. This is more for the technical people, but I would highlight one thing is that the polar field is a big question mark. It's a big question mark because if you're discussing with Sami, then apparently even the inputs for the magnetograms that he put are not that great. We are underestimating the flux. So you don't quite clearly know whether the driving of the model is also accurate. We don't quite clearly know whether the polar field constraints that we have in the model is quite accurate or not. So we do need a polar mission. There are multiple other challenges which are theoretical, but I'm again not going to go discuss them. but I'm happy to discuss them separately with those who are interested. And along with an advertisement, there's a completely different way to do this by forgetting about models, using a technique that Christoph proposed, which is an algebraic method for calculating the dipole moment. Sharnita, who's here, has a poster. I invite you all to look at her poster, which has also been used to make a prediction for cycle 25. Thank you.
So thank you very much. A couple of minutes for questions. Okay, I mean,
I can hear you.
Oh, not online. Okay. So I have a question regarding why we're predicting the solar cycle. Is it because we want to prove that we understand the sun a cycle in advance or 5.5 years in advance? Or is it because we want to predict project the infrastructure, such as, space weather? And if it's the latter, then why aren't we working on predicting a year and a half, 2 years in advance? And in that case, we have a lot of knowledge of what latitude the sunspots are coming, things like that. So I guess I don't understand the motivation to predict 5.5 years in advance.
So just quick answer to your question. When we began this work about 2 decades back, we were not so interested in the space weather aspect of it. For a theorist, for us who build models, I think the best test is prediction. So that was the motivation. But now I'm happy that Mark is using this more like the ensemble thing, where you are kind of updating your predictions on almost on a real-time basis. I think there has to be a marriage between the 2 approaches to do it the right way.
Hi, great talk. My question is also about different timescales of prediction, but in the opposite sense. Can you just say a few words about what you might expect changes the polar field on stellar evolutionary timescales, very long timescales?
Well, that's a tough question to answer, because we don't really have that many measurements of polar fields for stars. We have measurements of very large stellar spots, and even for the sun, we have so much confusion about what kind of dynamo is operating that I would really be sticking my neck out if I say the same dynamo is operating in other stars. That is certainly not the case. So I would say that the long-term evolution is more dependent on the slow change in the rotation rate and the differential rotation of stars, the breaking due to angular momentum loss, and that's the primary stuff that we are sure about at this point in time.
Nice talk, thank you. I have a question about the polar field measurements. You clearly indicated that they are essential for accurate predictions. What type of field measurements would you need for a polar mission? Should they be concentrated around solar minimum? How continuous the coverage should be?
Right. Okay. So ideally, we would. So what you see is only the R component of the dipolar field, right? The theta component is hidden. So you would need to see the radial field. That's the observable. We would like to see them. So near the solar minimum, it's all concentrated in a polar cap over 70 degrees latitude, and that flux is what we believe is being inducted in the deep interior to the toroidal field for the next cycle. So we would like to map the whole polar flux and reconstruct the dipole field based on that. Solar minimum is the best time if you have to allow me to choose only one time, but ideally we would like to see the whole process of the dynamics that results in even the reversal of the polar field, because that's where the fun is.
Okay, thank you very much. Thank you. So we continue the next talk, Christoph Petrovay, and forecasted for cycle 25.
Thank you. When I submitted my abstract, I optimistically expected that by August this year, we will have a fairly firm grasp about the amplitude of the ongoing solar cycle. That was based on the fact that for the better part of 2023, the smoothest sunspot number hovered in the range of the 120s. But then, as we know, the sun changed its mind, and in the last few months it produced quite a firework, which is still ongoing at this very moment, if you read the news last night. So I have to change the topic a little bit, and we cannot really confront predictions with reality yet, only with the most recent predictions that we currently have. So the two main centers where sort of official predictions are being routinely issued, Brussels and Boulder. Currently, most recently in August 2024, have these predictions. So on the left-hand side, you see the graphical plots, and in the table, you see the data. So the details of the different techniques vary. In the case of the SVPC, Mark Misch detailed this in his talk yesterday. But overall, these predictions are currently in the range 137 to 152. If you take into account the full uncertainty range, then it's wider. The details can be tricky, but I think I'm not telling you a big lie if I lump together all these methods as curve fitting. So basically, the sunspot number curve is extrapolated based on previous experience with sunspot cycle profiles. To put this range in context, the average cycle amplitude for all numbered solar cycles is 179, not very different from the average for the last 100 years that was shown to you by Diviendo in the previous talk. So compared to this, and also compared to solar cycle 23, which was almost exactly at this level, it's fairly sure that the ongoing cycle will be considerably weaker than the long-term average. And this is what was predicted by the overwhelming majority of forecasts. So at least in this respect, we can congratulate ourselves that we got it right, that this cycle will be another cycle significantly weaker than the long-term average. On the other hand, when it comes to the comparison with solar cycle 24, it's much less clear. Until recently, the general consensus was that this cycle should be similar or slightly stronger than solar cycle 24. What constitutes slightly stronger is subjective, of course, but as the average of cycles 23 and 24 would be around 150, so anything in the ballpark of 150 would be already in the midway between these two cycles, and would be hard to call slightly stronger. So anything significantly stronger than 140 would mean that we were not quite right in our predictions. So the current range just straddles this limit, and it's not clear what will be the outcome. So let's take a look at predictions issued earlier. Going backwards in time, the relatively most recent early predictions are based on the rise rate in the ascending phase of the ongoing cycle. These predicted an amplitude around 130. And then there are those predictions which are still based on internal properties of the sunspot number curve around the minimum or prior to the minimum. So there is a well-known correlation in the value of the minimum sunspot number and the upcoming maximum, but this correlation is pretty weak. And it has been pointed out that if instead of the minimum, we take the sunspot number 3, about 3 years before the minimum, then the correlation becomes a lot tighter, probably simply because of Poisson statistics. So these methods and methods analogous to these, which I like to call minimax methods, generally give predictions in the range 130 to 150, which is still quite compatible with the most recent predictions. All that happened was that this range has been narrowed down to the upper part of this interval. But then these predictions are still based on the properties on the ongoing cycle, because the underlying reason for this, as it was first suggested, I think, by Robert Cameron and Manfred Schüssler, and which I believe is correct, is simply that there is an overlap between solar cycles, as we know. So if the next cycle will be stronger, then because of the overlap, the minimum will occur earlier at a higher level of activity. So this is still based on the properties of the already ongoing cycle. If we look at real precursors or physical precursors, which are not based on knowledge that we have of the already ongoing cycle, then the primary precursor, as mentioned already in the previous talk, is the polar field or one of its several proxies. That in that case, previous experience shows that there is again a quite good correlation between the polar field or the AA index, which is one of its proxies, and the maximum sunspot area or the maximum sunspot number. Here's a collection of such predictions. Apologies if I missed somebody's favorite prediction. Overall, these tend to fall in the range 114 to 133. 114 was actually the amplitude of cycle 24. So these were definitely somewhat weaker than those predictions based on properties of the already ongoing cycle. Further, regarding model-based predictions, which were now discussed in detail, well, this was the plot that was shown to you by Dibiendu. There is actually a fifth one issued in 2021 by Chia's group. These fall in the range 89 to 126, so this is an even lower range. And it's interesting to note that there is an increasing trend. So the predictions issued earliest are the lowest. And this increasing trend seems to be generic. So basically what we have seen here for these different prediction methods is that the model-based methods yielded the lowest values around the same amplitude as cycle 24. Precursor-based methods predicted something like cycle 24 or slightly stronger. The minimax or methods based on the early progression of the current cycle are definitely in a higher ballpark, and the most recent ones narrow this further down. And actually, this may well be related to simply the epoch of these predictions. By epoch, what I mean is the date of the most recent data in the input data set, which is not necessarily closely related to the year of publication. So if we arrange all these predictions by the epoch, then there is an increasing trend observed, as you can see at bottom. So despite all the differences in the details, maybe the most critical property that issues them is that distinguishes them is how recent the data are that you take into account in your prediction. Thank you, should be enough. So this suggests that the sun just keeps correcting us. And the big question is there anything we can do about that? So is this something inevitable? We can just spread our hands and adapt to the behavior of the sun? Or could we have done better? And could we have done a better prediction early on? From this respect, it's interesting, if I only plot the precursor-based methods, then there is an opposite trend. I'm not claiming that this is a significant trend, could be a coincidence, but it turns out that the very early precursors issued before the time of the minimum was known actually tended to yield higher values than the precursors evaluated at the minimum. I think one of these early precursors will be discussed in the next talk by Bidyakara. Another factor which has not been considered is the alternation between even and odd cycles, which would of course fit a stronger cycle 25 than a cycle 24, which may need more attention. And finally, one property that is often missed in these prediction techniques is the asymmetry between the hemispheres. So in particular, in the previous solar cycle, cycle 24, there was a 2-year interval between the maxima in the northern and southern hemispheres. So if both hemispheres had peaked at the same time, then the amplitude of the previous cycle should have been considerably stronger, something like 140. So in this case, in the present cycle, where there is no such phase lag, we might still say that we are in the same range as the previous, as the amplitude of the previous cycle. I think I'll stop here.
Very much. Okay, so it's no. So online participants, please ask questions. You want your participation. Okay.
Thank you. I have very small comment when you about the long-term average of sunspots. When we refer to observe a sunspot number, it's really high because it includes solar maximum, but not solar minimum. I mean, grand solar minimum.
Yeah, the datum minimum.
Yeah, but if we consider the multimillennial or millennial scale, then the average solar cycle would be exactly what we expect now. So cycle 25 should be not below average, but just a fairly average cycle.
Okay, thanks. That's based on cosmogenic nuclei, of course, which may not be linearly related to sunspot number.
Thank you very much for presentation. And actually, I like your point when you discuss about correlation between activity during solar maxima on northern and south hemispheres. And my question is about solar minima, because we're discussing about importance of polar magnetic fields, but what we found in our work, actually accuracy of early predictions depend from time lag of polar field reversals. And can you comment on this? Do you see something?
You mean time lag of polar field reversals?
Yes.
Relative to, relative to what? The time lag?
What we actually found, if we have stronger delay in polar field reversals between different hemispheres, predictions usually more uncertain.
Well, yeah, I think the reversal is definitely important. So the original idea with this was that, well, after the reversal, the polar field starts to increase. So if you measure the rate of increase, then you can somehow predict the value of the polar field at minimum earlier than the minimum, if that's what you had in mind. And yeah, I think that's possible to do to some extent. I think in the next talk, Vidya will talk about such an approach. Yeah, so that's right. So I very much agree that the reversal is quite interesting and an important. Actually, what I showed here, but I didn't have much time to discuss, is that the reason why this 2-year phase lag between the hemispheres disappeared by this cycle was that in the northern hemisphere, actually the reversal took a very long time. The polar field hovered around 0 for something like more than a year, up to 2 years. Whereas in the southern hemisphere, it was quite sudden because there was this huge super surge, which was investigated in detail by Chia's group, in which a huge amount of new polarity flux just reached the pole in a single event.
Okay, thank you. Last chance, people online to ask questions. You can also speak if you like. Okay, thank you very much, Christoph. So next presentation, Vidya Karak. Is it Dr. Karak? Yeah. Oh, he's online. Oh, okay. That.
Okay, is it able to see my screen?
Okay.
Prasad, do you see my screen?
Yes, yeah, we see him. Yeah.
Okay, okay. So first of all, I thank the organizer for this opportunity to present my work here. So I'm going to discuss the predictability of the solar cycle using the rise rate of polar field. Exploration using observed data and the model. So this work was largely done by my PhD student Pawan Kumar and Akash Viswas. And here are the two publications. So I start by the presentation by reminding you the basis of the solar cycle prediction, which was already discussed by the two previous speaker. So in the solar dynamo, the poloidal magnetic field of a cycle, let's say N, okay, produce toroidal field for cycle N plus 1, which is through the omega effect. And this process is largely linear and deterministic because we know the differential rotation from observation. And then the toroidal magnetic field gives sunspot. And that means that if you know the poloidal field, or at least,
excuse me,
yeah.
Interruption. You need to share your slides because people otherwise don't see your share screen.
Okay, you don't see my slides.
We see in the room, but in online we have complaints.
No.
Okay,
now
that
Bilary is
okay,
also
they see now.
able
Okay,
to see.
okay,
So
please
it's
continue.
there's no problem anymore.
Okay, so let me. Okay, so I already. Okay, so now, do you see my screen?
Yes.
Okay.
Yes, yeah. Please continue.
Okay, so if you know the poloidal field, or if at least a part of it, then we can predict the amplitude of the next cycle. Okay, so usually the poloidal field or the polar field become strong near the solar minimum. Okay, and we take that value to predict the amplitude of the next cycle. Okay, so this is the basis. Now, the planning and preparation of any space mission takes several years, and the space organization needs to know the level of solar activity well in advance. Okay? And the current method can reliably predict the amplitude of the next cycle about 5 to 6 years, that is during solar minimum. Okay? The question is, can you extend this period at least by some amount? Okay? To explain this, let me show you this plot. So this plot shows the correlation coefficient between the polar field measured at the time tau after the reversal. Okay, so tau is equal to 0 is the time of reversal, and a different tau is that after this many years of the reversal, and this is the correlation with the amplitude of the this polar field with the next cycle amplitude. Okay, so you can see that that the correlation coefficient. Okay, so these are based on the observed data, and we have really limited data. Okay, so based on this data, we see that the correlation coefficient become exceed about exceed 0.8 in about like 4 years. Okay, and this vertical line shows the time of the minimum measured from the time of reversal. Okay, so this plot shows that you don't have to wait for the time of the minimum. The correlation coefficient between the polar field and the amplitude of the next cycle is becoming strong. Okay, a few years before the minimum. So this was from this work. Okay, and then we saw that instead of computing the polar field at a particular point, if we compute the rate of change of the polar field or rate of buildup of the polar field after its reversal. Okay. So in the bottom panel, we saw the absolute value of a polar field. So 0 value is the time of reversal. Okay, so polar time of reversal can be identified easily, and then we need to wait for 2 to 3 years, and it measure the slope of this polar field buildup. Okay, then this slope of the polar field rise rate, okay, is correlating with the amplitude of the next cycle. Okay, now here we have three data points. Okay, because we got 3 cycle from polar field data, and if you separate the hemisphere, then you have 6 data points. Okay, we cannot do much with this thing, but we got some correlation. Okay, So then the question is this correlation robust or not? Okay. So to check the reliability of this correlation, we use dynamo model, okay, and then SFT model. Okay. So first I'm going to show the result of a dynamo model. So for this, I use axisymmetric Babcock-Layton type dynamo model. I included fluctuation in the poloidal source that is in the Babcock-Layton process, and in the meridional flow. Okay. Then we compute the rise rate of polar field after its reversal and computed its correlation with the amplitude of the next cycle. Okay. So we get a strong correlation in the dynamo model. Okay. Now, in dynamo model, of course, we have some free parameters and we can still raise some doubt. Okay. So then we decided to conduct this study using SFT model. Okay. So in SFT model, we input the synthetic cycle. So we produce 30 synthetic cycle. Okay, so this is a typical cycle. So the how you generate this synthetic cycle is based on this Jiang et al. And Hatao et al. Work. Okay, so this is the monthly BMR number as a function of time, and this is the latitudinal distribution. Okay, so I'm not going through the details how we produce. Okay, so basically we try to mimic the observed features of the solar cycle, and we produce synthetic cycle and put this in the SFT model. Okay, so we take all the properties of the BMR from observation. So for example, the tilt, which is important here, the tilt we take from based on the Joyce law, which is this constant and then sine lambda, and then we have a Gaussian scatter around it. Okay. But while adding this scatter, we should keep in mind that we have certain fraction of anti-joy and anti-Hale. Okay, so this one is a normal the Hale joy BMR. Okay, so the tilt is measured with respect to the equator. Okay, so 0 to 90 degree is the range of the tilt, that is Hale joy BMR, and then we have about 10 to 30% anti-joy BMR, whose tilt is going from 0 to minus 90 degree. Okay, this is the picture, and then we have about 3 to 7% anti-Hale but joy. Okay, anti-Hale BMR. Okay, so the tilt for anti-Hale joy BMR will lie from minus 180 to minus 90 degree. Okay. And then the other properties are also based on the observation, but this is the important point. Okay, so then we do the simulation of the solar cycle using SFT model. So this is the radial magnetic field on the surface, and this is the polar field measured from 55 degree to pole. Okay, north and south separately. Okay, so then we compute the build-up rate of the polar field. So from the time of reversal to the to 3 years. Okay, within this period, I compute the rise rate of the polar field, and then I compute the correlation. Okay, so I consider different cases. Like in case one, I'm considering all BMR following Joyce's law, but I'm just randomly changing the amplitude. Okay, so then I compute the polar field again, and then the rise rate of polar field and the peak of the polar field. So we just see that there's a strong correlation. Okay, and then I took another case in which I randomly vary the meridional circulation in each cycle. Okay. But in this case, again, I'm considering BMR following Joyce's law. Okay, so just considering the variation in the meridional flow. Okay, so there also I'm seeing a strong correlation with the rise rate of polar field with the peak of the polar field. Okay, and then I'm considering the scatter in the BMR tilt. Okay, and I make sure that I have about 3 to 7% anti-Hale BMR. Okay, and about 10 to 30% anti-joy BMRs. Okay, and in this case, I am taking this anti-Hale and anti-joy BMR throughout the whole cycle. Okay, and then we again measure the rise rate of polar field and compute its correlation with the peak of the polar fields. Okay, so again, we observe a strong correlation. Okay, then I try to identify like in what phase the anti-Hale BMR impact the polar field more. Okay, so we realize that if we include the anti-Hale BMR, let's say all anti-Hale BMR, yeah, in the rising phase of the cycle, okay, then we do not observe much disturbance in the polar field. Okay, so that's why we see a strong correlation again with the rise rate of polar field with the peak of the polar field. Okay, so this is not difficult to understand because in the rising phase of the cycle, basically the half of the BMR, the poloidal magnetic field produced during the half of the cycle is mostly used to reverse the old polarity field. Okay. Therefore, the much disturbance in the polar field does not affect the amplitude of the polar field. Okay. And then I consider another case in which I am adding the anti-Hale BMR only in the decline phase of the solar cycle. Okay, so this means all 3 to 7% anti-Hale BMR are deposited in the decline phase of the BMR. Okay, so the number density of the anti-Hale BMR is actually large. Okay, even in that case also we see some correlation. Correlation coefficient decrease significantly. It is like about 0.8. Okay, and the reason is that during the decline phase, the polar field, the polar field produced from the BMR is used to amplify the new polar field. Okay, so that's why we see a little reduction in the polar field, but the correlation still hold. Okay, so from all this study, you can say that the rise rate of polar field, okay, statistically determine the amplitude of the polar field. Okay, and we know the amplitude of the polar field determines the amplitude of the next cycle. Okay, so we can make the prediction of the polar field just by measuring the rise rate of the polar field. So you don't have to wait for the solar minimum. You just observe at what time the polar field reverse. From that, you measure the rise rate of the polar field in 2 to 3 years. Okay, and then make the prediction. So if you do the prediction for cycle 25, then we get amplitude about 137 plus minus 23. Okay, so here is this the point that lies here. Okay, okay, so this is the prediction. Okay? Now, what is the connection here? Okay, what this tell? What this correlation tell? Okay, so we realize that the rise rate of polar field, as I said, the rise rate of polar field determines the peak of the polar field. Okay, this we get from the data from dynamo model, from SFT model, and then the polar field. We see the polar field determine the rise rate of the next cycle. Okay, and you know that if the cycle rise rapidly, it becomes a strong. Okay, so it is the Wallmeyer effect. Okay, and from the model also we see that the rise rate of polar field determines the rise rate of the next cycle, rise rate of the next cycle, next transport cycle. Okay, or the polar field determines the rise rate of the next cycle. So basically, all these correlation hold with the rise rate of polar field or the peak of the polar field. Okay, so in summary, it is the rise rate of polar field that determines the rise rate of the next cycle. Okay, this means that if you make the prediction based on just the classic Wallmeyer effect. Wallmeyer effect says that if a cycle is rising rapidly, okay, its amplitude becomes strong. Okay, so if you just follow that method, then we get a prediction which is shown by this black point. And interestingly, this prediction made from this Wallmeyer effect coincide with the prediction made from the rise rate of polar field. Okay? This again clearly says that these are actually interlinked. Okay? And that's why the prediction value also overlap. Okay, so here is my conclusion that we find strong correlation of the rise rate of the polar field build up after a few years of its reversal with the strength of the polar field at the cycle minimum, and the peak of the following cycle. Okay, and it is a robust features because we find it in the dynamo model, we find it in the SFT model. Okay, and this relation can help in slight early prediction of the solar cycle. You do not really have to wait for the minimum, okay, of the solar cycle. Okay, and here's the prediction, and here are my publications. So I'll stop here. Okay, thank you.
Okay, thank you very much. We have a couple of minutes for questions. It's any online, no online. Okay, more questions. Okay, okay.
Hello. Thank you very much for a nice talk. I have a comment. If you'll just compare the polar field measured in solar cycle 23 with polar field measured in solar cycle 21, then you will see that if zero time would be the reversal time, then they will coincide during the magnetic field will be coincide during about several years, but large difference will happen later. So the solar cycle 23 will stay with the same amplitude, but the magnetic field, the polar magnetic field in the solar cycle 21 would be larger and larger. And I think this is related to the activity of the solar cycle 23. Yeah. So it was not a question, it was a comment. That you need to know how behave the polar field much later than the reversal time.
Yeah, so so it is true. Okay, let me make one clear comment that the prediction based on the rise rate will give only early prediction. Okay, if you are lucky, sometime it may work, but it's in statistical sense it will give an early indication. But if you want to make a more accurate prediction, of course you need to wait for the peak, wait for the time during the solar minimum. Okay, as you see from the last few cycle, I mean we have only three cycle. Okay, so if during the in fact actually the answer is largely here. Okay, so the correlation, as I said, like if you put lot of anti-Hale BMR, okay, which produce opposite polarity field, okay, towards the end of the cycle, that can disturb the polar field, the strength of the polar field. Okay, and that's why you are not getting a very strong correlation, and you see the correlation coefficient is decreasing significantly. Okay, here I took a very worst case scenario. I added all the anti-Hale BMR that you typically see in one solar cycle. Okay, so you are right. Yeah, we have to be careful.
Okay, thank you. Hannah, introduce yourself.
Hi, Pidia. Thanks for that comprehensive talk. This is Hannah Shunka. I have a question about your plot with the green lines in it, which you just showed, and you talk about the rise rate. I can't see a difference in time for that rise rate. Can you explain the uncertainty there? And if it is the same for all the cycles, the time taken to reach the peak polar field is the same?
Okay, so the green line shows that, so I added this line by hand. Okay, so the idea is that after the reversal, I took one point after 3 years. Okay, and then during these 3 years, I computed the difference in the polar field. That is like okay, here the polar field, the starting value is 0, and then it's basically the you need to take the polar field after 3 years from this. Okay.
Okay, so the time, is the same for each.
Sometime like for this cycle, in 3 years, actually the polar field, reach to the peak. Okay, but in some cycle, it takes a few more years.
Okay, thank you very much. So now we have brief poster presentations. Could you please show the first slide? So we have, you can see now what people who submitted slides for 1 minute presentation. So if you're in the audience, please come here. So I'll be advising slides. Is anybody here to present slides? So just stand in line in this order. And Daniel, I know he sent email that he cannot be here. So please, okay, I'm advancing slides. So that please look at Daniel's poster. And he was not able to come here. Also, it's because of time zones, he's not able to connect here. So let's go to the next slide. And next slide is recorded. Could you please play recording? Next presentation.
Good afternoon, everyone. Here I present few slides corresponding to my poster titled Non-Equilibrium Radiative Transport in the Solar Chromosphere. As you might already know, when you go to the solar chromosphere, the approximation of local thermodynamical equilibrium for representing radiation field doesn't hold good anymore because the scattering of radiation on atoms become important. Further, when there is dynamics, that is when there is a shock passing through the atmosphere, the ionization and recombination timescales are so different that even the kinetic equilibrium equation doesn't hold good anymore. The rate system becomes time dependent, which is represented by this equation in this slide. N are populations, C and R are collisional and radiative rates, and all of them are time dependent. And on the right, you have a time derivative of the population and advection term. With this generalization to time, the radiative transfer module is developed for the radiative MHD code model, and the comparison with the stationary solution validates our numerical method and is presented in this paper. Here the validation is shown. What is plotted is electron density, ground state of hydrogen, first excited and ionized state of hydrogen as a function of height. The dashed lines are produced by the RH code, which is another publicly available independent well-tested code which gives us stationary solutions. This is by Altenburg 2001. And we keep all other hydrodynamical quantities constant and let our non-equilibrium system start with LTE solution but let it evolve, and it eventually, as shown here, reaches the equilibrium solution.
Okay, so the next, who's the next?
Good morning, I am Valente, and this will. Okay, I am Valente. Good morning. I'm based in Portugal, and my motivation is to analyze the solar flare based in 3D models. The magnetic field is modeled as a dipole, and we calculate the Gauss-Singleton equations. And we constructed a database of more than 300,000 elements, and we fit the model using forward fitting based in literature of based in literature analyzed flares. That's it.
Hello, I'm Divya from Arizona, India. So here in this work, we have estimated the polar magnetic field. So yeah, we use the Kodaikanal Solar Observatory calcium K data from 1907 and also Rome PSPT data, and we have used the polar bright points as proxy to reconstruct the polar magnetic field information, and also we calibrated with the Wilcox polar field and FT polar field to estimate the polar magnetic field. And this is the results. So we have estimated the polar field starting from the 1907 to 2022, and also compared the current polar magnetic field. Thank you.
Okay, Gregory, you're online?
I'm here.
Oh, here.
Okay, hello everyone. I'm Yuri and I'm from Belgium. And I want to study the impact of the inclination angle of the rotation axis and using direct observation of the sun. So we have the solar chromosphere, and then the first step is to segment the brighter structures. Then with those structures, we we construct synoptic maps to map the entire solar surface. And then based on those synoptic maps, we have reconstructed solar images from any inclination angle, from the North Pole view to the South Pole view. And what we wanted to study with this is to know if we can detect modulations from the solar rotation period timescale or the solar cycle timescale. And so for this, we have extracted the area fraction of the structures based on the inclination. And here we have the result of the area fraction. Of course, it's decreasing from the equatorial view to the polar view. And if you want to see the result of the detection of the modulation, come to my poster. It's not 73, this was the morning, it's 87. Thank you very much.
I'm here online. Can I speak? Are you able to hear me?
Anna, are we online?
Yeah. Can you hear me? Hello?
Yeah, please speak.
Okay.
I'll get once in your
You
slides.
can just move the slides. Hi everyone, I am Anup Sridevi. I am from India, and I have two posters in this session. So the first poster is this regarding an automatic algorithm that we developed for tracking the bipolar magnetic regions from line of sight magnetograms. So just can you move the slides, please? So it basically works by, initially starts working by automatically, not this, the previous slide. This is my second slide. I think you have to go back. Okay, yeah, I'll talk about, So the title is Auto Tap, not this one. So
yeah, please, when you do this, please don't make these transitions. It's very difficult.
So basically, I have an automatic algorithm which it starts by detecting the BMR automatically from line of sight magnetograms, and then we check for its presence in future instances. So that's how we detect and track the BMRs, and by this method we tracked for almost 12,000 unique BMRs for the period of 1996 to 2024, and we were able to recreate the butterfly diagram and the solar cycle variation. In my next poster, using the catalog developed, the tracked information developed from the AutoTap catalog, we try to evaluate the validity of thin flux tube model for the formation of BMRs. As everyone knows, the thin flux tube model assumes magnetically buoyant flux loops anchored at the convection zone, rising through the convection zone to the photosphere, and the Coriolis force attributes to the tilt in the BMRs. So we find that over the evolution of the BMRs, the foot point separation increases, suggesting that validating the assumption of rising flux tube. And we find that for lower flux regions, the average Joyce-Law slope increases with the flux, and for higher flux regions, Joyce-Law slope decreases with the flux. And similar trend is observed with the Bmax. And coming to the, we also find clear Joyce-Law trend from the first detection of the emerging BMRs, suggesting that at least some tilt observed in the BMR is from the Coriolis force. And where all in all, in my conclusion, my analysis validate thin flux tube, give some support to the thin flux tube model. For more information, just visit my poster or write to me. Thank you. Thanks.
Okay, thank you. So by the way, during poster session, connect also online. And if there are cameras there, and if you see people looking at your poster, you can start talking to them. And also all presenters can actually talk to people who look at your posters that's online. So look at, connect and look at the camera event, who is looking at your poster. Okay, next.
Hello everyone, I'm Vindhya Vashish from IIT BHU, Varanasi, India. So in this work, I'll be explaining the role of meridional flow in the generation of solar stellar magnetic field. So as we know, the meridional flow, it's important in generating the poloidal field on the sun and sun-like stars. And this meridional flow affected with the rotation rate of the star as well. And it affects the activity and the cycle period. So in this work, I have used a 3D dynamo model, and I started with this evolution of the single BMR, like how a single BMR will evolve during time. So as you can see, for a single BMR, if we start with a low meridional flow, then the trailing polarity will be like move faster, like efficiently towards the pole. And as the meridional flow increases, it will the trailing polarity will efficiently increase to the polar field with the polar region. But after a certain point, both the polarities will move towards the pole and hence will cancel each other near the pole. Because of this, the polar field decreases after a certain point. So this increasing and decreasing trend was also observed in different, like to check the robustness. I also checked in different scenarios, and I've checked this in a dynamo model as well. And I've implemented it in a stellar cycles. Like I've taken the meridional velocities, meridional flow, and for hydrodynamic model, and I've checked, change the rotation rate of the star, and I have actually changed the depth of the convection zone as well. And yeah, this is the conclusion, and you can actually scan the link to check my paper. And in my next work, this is basically the similar work, but in the 2D dynamo model, in which I have checked the variability of the sun-like stars, like how these stars evolve in a long duration, like for 11,000 years, how these stars will behave. So we successfully find the magnetic activity trend in our using this model. We have successfully find the magnetic activity trend and the cycle period as per observations. And the important result from this work is the variability. As you can see, as the rotation rate, as the rotation period increases, the number of grand minima, like the Maunder minima like event, is increasing. And we can conclude that the slow rotators show more variable cycle, show frequent grand minima, and rapidly rotating stars experience strong activity with irregular cycles and no grand minima at all. So thank you. You can visit my poster downstairs.
Okay, thank you.
Hi, this is Srinjana here. So my poster is on the dynamic rotational profile of the solar atmosphere. Now we I'm sorry. This one, right? Okay. So all of us know that the photospheric differential rotation profile is very well established, as well as the solar interior rotation profile from the modern endeavors of the helioseismology data. But as we go higher in the solar atmosphere, especially let's take chromosphere, for example, there is a clear debate as to whether chromosphere rotates faster or slower, as has been established by this particular data set, which two different studies have adapted. And one has found faster rotation, one has found slower rotation. There are plenty of examples for this in literature. And so that is why we aimed at a comprehensive study using space-based data, and we have used the method of image correlation, where we have taken two consecutive images temporarily separated by 6 hours and have been map them in heliographic coordinates and bind them according to latitudes to find out the correlation coefficient for which the value of correlation coefficient is maximum, and corresponding to that shift, we have calculated the value of the rotation rate omega. Now, this method, after applying to the several data sets, several wavelength channels, we find that the hotter solar atmosphere does rotate much faster than the solar photosphere. When we looked at the equatorial rotation rates closely and its variation with latitude, with depth and altitude and temperature, we find that equatorial rotation rate actually increases, and we also find a signature of decreased differential behavior as one goes higher in the solar atmosphere. Incidentally, we have also found an interesting match when we compared the equatorial rotation rates of the solar atmosphere with that of the solar interior, more specifically the convection zone. And when we looked at the temporal variation, we also have found a very good correlation of the equatorial rotation rate as well as the differential gradient with time, suggesting probably, as has been predicted by some previous studies, as to torsional oscillation probably. So these are the summary and the conclusions of our work. You can find my poster downstairs and screen number 36, and also catch me up at any time soon. And thank you for that.
Oh, thank you very much. Okay, this concludes our first session. So thanks all participants and all presenters. Thank you very much. And so we reconvene at 1:30.
first give a brief introduction to the mission and the 3 payloads. Then in the second and the third parts, some representative observations by these 3 payloads will be presented, especially for the observations related to the series of X-class flares in May this year. And the final part are the selected early results. And actually, the mission has a Chinese nickname, Kuafu. And actually, he is a man who was chasing the sun in all his life in one of the Chinese fairy tales. And the mission was proposed by Dr. Gan in 2011, then officially approved at the end of 2017. It was launched in October 2022. Then in April last year, we released the data for most of the instruments and together with the software and tutorial. And the mission has a sun-synchronous orbit with a nominal life more than 4 years. Its scientific objective is to study 1M2B in short. And 1M means magnetic field, and 2B are the 2 burst flare and CMEs. And to observe the magnetic fields, flares, and CMEs, we have 3 payloads on board. FMG is a 4-disc vector magnetograph, and HXI is a hard X-ray imager, and LST is a Lambda Alpha Solar Telescope. And the locations of these 3 payloads on the satellite platform is shown on the left, and the observing targets of these 3 payloads are shown on the right. HXI observes the magnetic reconnection region, the flare loops, footpoints, and the ribbons. LST observes the CME prominence, loops, and ribbons. FMG observes the photospheric magnetic field, and from where we can extrapolate the chronomagnetic field. Some key parameters of the instrument. FMG has a 4 sun field of view and observe at the iron 532 nanometer spectral line, and the time cadence is about 2 minutes. HXI has a energy range from 10 to 300 keV with a spatial resolution about 3 arcseconds. The cadence is from sub-seconds to 4 seconds, depending on the observing modes. LST consists of 3 instruments. WST is a white light solar telescope. SDI is a solar disk imager, and SCI is a solar corona imager. And WST and SDI observe the 4 disk at 360 and hydrogen Lambda alpha respectively. And the field view is up to 1.2 solar radii. The cadence in its burst mode is about a few seconds. In routine mode is from 1 minute to 2 minutes. SCI is a dual waveband chronograph in UV Lambda alpha and white light. It has a field view from 1.1 to 2.5 solar radii. The second part of talk is to show what these 3 payloads can observe. FMG can measure the longitudinal photospheric magnetic field. In the left image is the subregion HMI line of sight magnetogram, and on the right is the same region observed by FMG. They are almost identical. Unfortunately, FMG lacks routinely observed 4-disc and vector magnetic fields. And also we can use the FMG data to investigate the magnetic field evolution of an active region. For example, here, the emerging magnetic flux can lead to a solar eruption. HXI provides hard X-ray spectrum and imaging, and this figure shows the hard X-ray sources at the flare ribbons, post-flare loops, and also in loop top. Its performance is exactly the same as, or even better than that designed. Also, we compared the HXI light curve with the sticks on board the solar orbiter. We can see that they are consistent, and also the imaging from these two instruments share some similarity. Considering the separation angle between the Earth and the solar orbiter was about 20 degrees. And LST provides the Lambda alpha 4 disk and the inner corona image, and observe the inner corona in Lambda alpha and white simultaneously. In the left image gives an impression of what solar features look like in Lambda alpha line. For example, Lambda alpha prominence, CME wave flare filament, and also I include here a white light flare. Unfortunately, the spatial resolution of the 4 disk images and the straight light levels of the chronograph are not as expected. Nevertheless, we have captured quite a number of CMEs by the chronograph. And here are some further observations of LST. And on the lower left, we see the simultaneous observations in white light and the UV of a CME with prominence as its core. And here showing some prominences with different morphology observed by SCI UV. Then let's go to the observations related to the series of X-class flares in May this year. And particularly, we are interested in this super active region, 3664, and its associated sunspot group reach a maximum area more than 27 millions. Then the magnetic classification is also the most complicated type, the beta, gamma, delta. And on the right is the HXI spectrum indicated by this vertical line in colors for the major flares in a time window of 10 days. And to get an overview of how this superactive region evolve across the solar disk, I included here the 4 movies of the sun at different layers from photosphere, chromosphere, and also the up transition region. And in the bottom row are the 2 examples of white light flares and Lambda alpha flares. If we want to go to the detail of where the hard X-ray locates and how the spectrum look like, we can combine HXI and AIA images. And most probably these series of X-class flares are driven by the extremely complex magnetic field and photospheric evolution. And also we have captured the series of CMEs observed by SCI-WL. And this slide shows the joint observations of SCI-UV, the prominence, with the Chinese DART radioheliograph observations. And finally, some selected early results. And most of the early results are published or going to be published in this solar physics topical collection. And we have also published 15 papers in other journals. And here are some selected ASO early result. We have studied white light flares, and we find from our statistics study, we find these white light flares at 360 nanometer are not rare. Its occurrence probability is about 24% for the major flares larger than M1 class. And it will provide an important reference for stellar flare studies. And our case studies shows that the Balmer continuum radiation at 360 comes not only from the flare ribbons, but also from flare loops. Now let's go to the white light radiation related to the 12X class flares from this superactive region. And to show the flare ribbons and loops, we plot in green the AIA 1600 angstrom image, and in red the AIA 131 channel, and the HMI white light emission are indicated by the blue contours, and they are either located along the flare ribbons or along the flare loops. After checking the WS data carefully, we found that 11 out of the 12 X-class flares are white light flares. And if we compare the Balmer continuum observed by WST with the Paschen continuum observed by HMI, we find that the WST white light flare usually has a larger area and a greater enhancement. And the hard X-ray sources indicated by cyan colors usually located at loop foot point or the loop top when the flare are beyond the limb. And these are some details of the white light flares, including morphology, source, duration, and also enhancement percentages. And from the light curves, we found various relationships between the white light emission and hard X-ray emission for the peak time. And concerning the hard X-ray observations, we have observed maybe the clearest sliding process of a hard X-ray source on a flare ribbon. And the origin of the QPP oscillation in this flare is from the sliding magnetic reconnection modulated by the magnetic field. And we have also made the first 3D analysis of hard X-ray sources combining STIX and HXI observations. And this work benefits from the collaboration via the ASO-S guest investigator program. And for the SDI observations, we observed for the first time the Lambda alpha waves by SDI, and the study of the Lambda alpha, H alpha, and the EUV waves shows that a very tilted eruption plays a key role in the formation of lower layer waves. And observations and the radiative transfer calculations show that the spatial position of the Lambda alpha wave is closer to that of the H alpha waves. I think I will stop here by showing the links to the ASO-S data and software web pages, and also the guest investigator program, and also the contact information. Thank you very much.
Questions online? Okay, questions? Yeah, please introduce yourself because people online, they don't see us.
Yeah, thank you very much for a very interesting talk, and congratulations for the success of the launch of first solar mission in China.
The second one.
Second, I'm sorry. And I'm impressed by the observation of white light flares. And did you make a correlation plot between hard X-ray intensity and white light intensity?
Not yet. Now we have just plot the location of the cyan color is the location of the hard X-ray, and the white enhancement are the white light flares. And the next is just some a comparison between the peaks of the white light and the hard X-ray. And maybe in the future we will
I see.
compare
So
the
yeah, I want to hear the comment on the physics of white light flares, but still not yet.
Yes, for example, the heating mechanism, the alpha wave, electron beams, proton beams, yes, many different mechanisms.
Okay, I'm looking for future development
Thank
research.
you. Thank you.
Okay, thank you. More questions? Yeah, that what I noticed that your white flares distributed mostly close to the limb, if you look at distribution. And then the question is, it's about the definition, what you call white light. Is it just Balmer continuum? This it's a long-standing question since Trace mission.
Yeah.
That what you call white light? Was it integrated white light or just Balmer continuum? Then near the limb probably you see some higher layers in the atmosphere heated and not real continuum, not real white light.
Yes, and on the disk, usually from the Balmer continuum, and here beyond the limb, maybe some Thomson scattering may contribute the white light.
So when you can see in Balmer continuum, we call it white light.
Yeah.
Okay,
In
okay.
principle, yes.
Okay, more questions?
Okay, Irina Kitiashvili. Very interesting talk. Sorry if I misunderstood something, but I got impression what you measure magnetic field in solar corona.
No,
because on one of your movie you indicate like magnetic field to Gauss. It was like on your movie with kind of okay.
It's only the photosphere, the photospheric magnetic field.
Okay.
Yeah, we maybe it's our future, the coronal magnetic field measurement.
Okay, more questions? No online. Okay, thank you very much.
Thank you.
So the next talk is online. Savita Mathur. Savita, you're online?
Yes, yeah, I'm here.
Just please show slides and she will talk.
Okay, I had sent
a
a
recording. It will be your slides and.
So I had sent a recording. Should I?
You can try to share slides.
Okay, let's see if it works. Can you see my slides? Let's see if I do this. Can you see the slides?
Yes, yeah, it's good. Yeah, thank you.
Okay. Okay, hi everyone. I'm very happy. I want to just thank the organizers for giving me the chance to give this talk, for inviting me to give this talk. Unfortunately, I couldn't come, so I'm right now in Boulder. So it's a bit early here, so hopefully it will go well. So yeah, I'm going to talk about the observational constraints that we can get from helio and asteroseismology for dynamo models. So first, I just wanted to remind you a few things about seismology, some basics. So you know that there are different types of modes that we can see in the sun and solar-like stars, like the acoustic modes for which the restoring force is pressure. They are excited by the convection in the outer layers of the solar-type stars. So you can see some example on the video on the left. Then you have gravity modes for which the restoring force is buoyancy. They're also excited by the convection with plumes going into the radiative zone, and they are propagating in the radiative zone and evanescent in convective regions, like the waves you can see on the left. And then you have another type of modes that result from the two previous ones, which we call mixed modes. And they behave as acoustic modes in the envelope and as gravity modes in the deep interior, radiative interior. And so they probe both the core and the envelope of the stars, and they're very interesting, as I will see in the next slides of my talk. So these modes are characterized by 3 quantum numbers: the degree L, that gives the number of nodal lines on the surface of the star, M, the azimuthal order, that gives the number of nodal lines that cross the equator, and then N, the radial order, that's the number of nodes you have along the radius of the star. Okay, so first I wanted to show you the effect of rotation on the modes. So this is an example of our L = 1 mode, where you can see that there's a lift of degeneracy, and you have 3 components that can be observed. And the faster the star is rotating, the larger this rotation is splitting, the distance between the components will be. This will also depend on the inclination angle. So you can see how the ratio between the components of the amplitude of the components will change depending on the inclination angle. So for the sun, we have thousands of modes that can be observed, because we can resolve the sun. And so we have splittings for all these modes, and thanks to inversion technique, you can infer the solar internal rotation. So here you have an example of the rotation rate as a function of the radius, where you can see the latitudinal differential rotation in the convective zone, the solid body rotation in the radiative zone. Unfortunately, we don't know exactly what's happening in the core, though some detection of signature of gravity modes seem to say that the average core rotation in the core is around 4 times faster than the surface. So one question that we can have is the internal rotation of the sun typical. So that's one of the things that we also want to try to understand. So going from helio to asteroseismology, what happens is that we don't have so many modes that we can detect because we don't resolve the stars. So we have only low degree modes, so L = 0 to 1 and 2, and sometimes 3. But still we have like now thousands of detection of solar-like oscillations in main sequence to subgiant stars. This is the picture for a nature diagram for solar-like stars on the main sequence at subgiants. We have thousands of detections, and on the right you have the state of the art for the red giants, except I didn't put the test targets yet, but we have more than 200,000 stars with detection of oscillations, solar-like oscillations. Okay, so and this was done with missions like Kepler, K2, and TESS. So one thing that we can do with helio and asteroseismology is to infer the internal structure of the sun and the stars, either by using stellar modeling, where we have individual frequencies of the modes that allow us, for instance, to have the depth of the convective zone. However, this is model dependent. We can also use inversions technique. Many works have been done in the past for the sun. This is an example on the bottom for the sound speed profile for the sun. And now there are more and more new techniques that are being implemented using MCMC frequency ratios, providing a lot of new results for the sun and solar-like stars. But I wanted to focus on rotation, which is one of the important ingredients for dynamo model. So one of the things we want to see is if we can measure latitudinal differential rotation. So several works have been done to look for this kinds of signature in solar-like stars. I will be highlighting the work by Benomar and collaborators in 2018, where they looked at the Klebsch-Gordon A coefficient for their rotational splittings. So actually the A3 coefficient has information on the latitudinal differential rotation. So they measured in this work the A3 component for 40 solar-like stars observed by the Kepler mission. Here in the bottom, you can see the distribution of this detection probability for all these stars. What they found was that, so on the left, you have the anti-solar rotation, differential rotation. On the right, the solar rotation, differential rotation in blue. But they found the most significant detection for only 13 stars, which are the ones with solar-like rotation, differential rotation, and nothing on the anti-solar rotation differential. So it is difficult, but we are trying to work on this, and hopefully in the future there will be more precise data to do this. Then if you move on to more evolved stars, you have these mixed modes that I talked to you about early on. And as I said, they probe both the core and the envelope of the stars. So in this work, the Hovels and collaborators looked at the rotational splittings for some subgiants. On the left, you can see the power spectrum as a function of frequency for different frequency ranges for a single star. And you can clearly see the splitting of the modes and how, as a function of the frequency, when you go to lower frequency, the splitting, the distance between the components is changing. This is clearly visible by eye. So on the right panel here, you can see this rotational splitting as a function of the distance to the L=1 theoretical ridge. So on the left, you have modes that are more acoustic dominated mode, whereas on the right, more gravity dominated modes. So they're probing the core on the right and the surface on the left. And so this suggests that the core is rotating faster than the surface. So this was also applied to red giants. Here is an example of the work by Moser collaborators in 2012. Again, you have the rotational splitting as here as a function of the radius. You have the RGB stars with the crosses, and then here the triangles are the red clump stars that are burning helium in the core. And what they found was that maybe there was a slight spinning down of the core rotational rate on the RGB, and then a clear decrease for the red clump stars. Later on, Jean and collaborator analyzed in a more statistical way a larger sample of stars. And here the picture was less clear on how the rotation rate of the core was changing with the RGB, which are represented with the triangles. And so it's more flat and it doesn't seem to be mass dependent. Whereas for the red clump, we see also, again, that there is a clear spin down. Okay, so the next part of my talk was on magnetic activity. So we can also use seismology to study the surface magnetic activity of the sun. So here we have the Virgo instrument flux as a function of time, here time frequency analysis and kind of projection of the wavelet power spectrum here on the time axis. And you can clearly see the magnetic cycle of the sun. On the right, you can see how the amplitude of the acoustic modes and the frequencies of the modes are changing during one cycle for the sun. There is this very nice anti-correlation that we see between the amplitude of the modes, the sunspot number, which is the red line here, and the frequency shift. So this was also detected first in a Coro target, HD 49933. We saw this very nice integration again between the amplitude of the modes and the frequency of the modes, suggesting that there was a cycle going on in this star. And we also did some complementary follow-up, spectroscopic follow-up, where we had calcium HK observation measurements showing that the star was indeed active, and maybe some cycle. Unfortunately, we didn't have enough data to confirm the length of the cycle. We can also study more effect, like the metallicity effect on magnetic activity. This was done with this Kepler target, what we call Doris, which is very similar to the sun in terms of radius, mass, log G, age. So here you have the chromospheric emission on the left, on the top left panel for Doris, and then on the sun. They are both on the same scale. And then you have the relative photometric flux, frequency shifts for different degree of modes, the amplitude of the modes, and proxy of the photometric activity on the bottom panel. One thing that you can notice, so the star is known to have a 7.4 year cycle, shorter than the sun. And the other thing you can notice is the amplitude of the cycles, which is much higher for Doris compared to the sun. And so if you go into the details, the star is actually metal rich compared to the sun, 0.3 dex. And this will lead to a deeper convection zone, more vigorous convective velocities leading to a stronger differential rotation, and as a consequence, stronger chromospheric emission compared to the sun. So that was a very nice result, that we can probe different effects of stellar properties to study magnetic activity. And such study was also done for close to 100 Kepler solar type stars now, led by Santos et al. In 2018, where they also measured these frequency shifts. And you have the distribution of these stars in this HR diagram. And again, you can study how, because we have asteroseismology, we can have the ages of these stars, and you can see how the magnetic activity decreases as the star evolves. And we also found here in this diagram that, again, when stars are more metallic, they have a stronger cycle. There are also the works on looking for active latitudes constraints, but I don't have time to talk much about this. Okay, so then if we go into the more, again, staying in the evolved stars, but clicking into the internal magnetic field, there are two different works that have been done. One of them was started because there was these very weird anormal dipole modes that were found in red giants with very low amplitude. So here you have the visibility of the modes as function of the frequency of the maximum power. And you have these stars with suppressed dipole modes. You can see some example of power spectrum here. So you have the helical one modes in red for a normal star, and the suppressed one, you can see how the amplitudes are very small compared to the normal star. And one explanation, theoretical explanation for this, was that there was a strong magnetic field in the core of these stars that was breaking the spherical symmetry and leading to alpha n waves, a very high degree L modes, which were trapped in the radiative zone. And so they had, this could lead to a low amplitude of the modes. So this was work done by Fuller in 2015, but later on, Stello and collaborators looked at how the distribution of the masses of these stars were, and the stars with suppressed suppressed L=1 mode, sorry, were stars with that were more massive than 1.2 solar mass, which corresponds to the transition from the from having convective core during the main sequence, which could be coming from dynamos that were happening in the core, leading to this very strong magnetic fields. Of course, there are some controversial results on this, and there are also other possible mechanisms that were involved still with magnetic fields. So this is still some work going on. Another way of detecting internal magnetic field is by looking at the mixed modes. And so I told you that there is this lift of genericity due to the rotation. So you have this, for this L=1 mode, you have 3 components, the triplet, but magnetic field will also lead to a shift of some of these components. And this is the case for an axisymmetric magnetic field. And you can see that the shift will not be the same for all the components, leading to an asymmetric mixed triplet that you can also see in this diagram with the frequency on the modes, as the splitting of the modes as function of the frequency. So this was done developed by theory by Matisse et al., Lebonier et al., and Loy et al., and then it was generalized to a magnetic field without a priori assumptions on the topology, and this led to the discovery of asymmetries in the splittings of several red giants. So this is a work by Lee and collaborators and Devers and collaborators. Here you have an example of a power spectrum with the splitting of the modes, and you can see this clearly the asymmetry of the splittings, suggesting that there were fields from 30 to 100 kilogauss in the core of these red giants. Okay, so this leads me to the conclusions. So we saw that with seismology, you can have internal structure, the information on the internal structure of the stars. We have also measurement of internal rotation of subgiants and red giants, which is very exciting, which is more than what we know for our own sun. So the cores seem to be rotating faster than the envelopes, with some discussion on whether the core during the RGB is spinning down or not. Magnetic activity cycles can be detected with seismology thanks to the frequency shifts and the changes in the amplitudes of the modes, but this also means that magnetic activity can prevent the detection of the modes if the stars are too active. The internal magnetic fields have also been measured in red giants with the split asymmetries of the splittings. And I didn't talk about local Helios seismology, but a lot of work is being done to study subsurface structure, torsional oscillation, etc. So in terms of asteroseismology, especially, we are in this era, a new era where we're doing a lot of new exciting discoveries, and Plato, in particular, will in the future will provide many more detections, I think, with tens of thousands of stars, so that we will be able to study very deeply. So stay tuned, and we hopefully will have more constraints for dynamo models. Thank you.
Okay, thank you very much. So any questions online? Please raise your hand. Okay, Alfia. Unmute your microphone and speak.
Hello?
Yes. Yeah, Alfia.
Thank you very much for this nice talk. I want to make a comment concerning this Lowy-Papaloizzo work that you have mentioned. Has been proved that this does not work. It is impossible to stabilize a toroidal field only with a poloidal field in general. We, with Gustavo and others, have proposed and have demonstrated that the gravity should be the main stabilizing effect in the core of red giants. And so far, that is I would say that is an important mechanism that would also provide topologies of the internal magnetic field, which is much simpler and much more prone to be proved with asteroseismology than the mixed field configuration, which has been then found that is not stable. Okay, that's my comment on your work.
Okay, thanks. Yeah, as I said, there is a lot of controversy on all of this. So
no, there is not much controversy. I mean, this Lowy-Papaloizzo model has been really shown that it's unstable. If you look at the reference and things like that, unfortunately, that does not work. So that I think is more or less clear.
Okay, thanks.
Okay, thank Alfia for comment. Emre Isik.
Hi, thank you for the nice talk, Savita. So concerning this magnetic activity increase due to metallicity. So in that case, for instance, the star that you looked at had, as I noticed, a shorter rotation period. So it was about 21 days.
Yes.
So can you evaluate, or you tested how much effect on the magnetic activity comes from metallicity and how much from the rotation period decrease with respect to the sun? So faster rotating stars are can be slightly more active. And did you also check the photometric variability there? Last question.
Okay, so for the effect of metallicity, I mean the rotation. So I mean I think we didn't check all of this, but that's a good point. There is the effect of, there are many works like Louis Amar and others who show that metallicity will also affect rotation. So I think there are a lot of things we can indeed do with all of these stars. Now we are having more larger samples, so maybe we can start to do a lot of things on this. So yeah, that's a very good point. So for the photometric activity, are you talking about like
variability amplitude?
Variability in the photometric data with Kepler?
Rotational timescale. Yeah.
Yes. So that's what we're doing with the SPH here. So this is
Yeah.
Like the standard deviation in small boxes of 5 times the rotation period as a function of time. And you can see here that it was increasing while it was also increasing in the chromospheric activity. So these are contemporaneous observations. And it is much larger for this star compared to the sun. So yeah.
Yeah. Yeah, thanks.
Okay, thank you. High metallicity generally means a deeper convection zone, so it may be that it relates to. I also have a question about this star. One of my students found flares, kind of big flares on this. Do you know about somebody else found this?
Okay. No, I don't think I've heard about flares on this star, so that's very that's
okay.
very nice. Thanks. Maybe we can talk later.
Okay, more questions? It's more questions online. I have a question about this suppression of L=1 mode, that what you explained with magnetic field, but also L=1 mode on subgiants, it's a mixed mode. And mixed mode, because it's part of these oscillations in the core, maybe just not enough excitation at the surface to get high amplitude for L1 mode.
So this was mostly for early red giants and late red giants, but there are some stars where actually there are, especially I think that was seen in mostly subgiant stars where you can also see a kind of half suppressed, so we call them droopy-like, so they have normal L=1 modes up to nu max, let's say, and then they are depressed below a given frequency range. So yeah, but I don't think we've seen suppressed L=1 modes for the subgiants. That has not been completely suppressed. No.
Okay, thank you. Okay, if no more questions, then thank you very much. Okay, next talk is Hannah Schunker, onset and evolution of Joyce law.
Okay. Confusing. Okay. Good afternoon. It's a pleasure to be here. Thank you to the organizers for giving me this opportunity to talk about work a graduate student, William Roland Batty, has been working on with me to model the onset and evolution of Joy's law. So Joy's law states that the leading polarity, so the polarity in the direction of rotation of an active region, tends to be closer to the equator than the following polarity. So this is not true for all active regions. There are some that follow Joy's law, and there are others that do not. But on average, statistically, this is true. In addition, this tilt angle increases with latitude. So active regions that appear at higher latitudes have a higher tilt than those closer to the equator. They're less tilted, which gives the idea that the Coriolis force is responsible for Joy's law. And Joy's law is an important component of some dynamo models. Some, yeah. Okay, good. So in the past, we have, the thin flux tube model has explained Joy's law very nicely. There is a flux tube placed at the base of the convection zone. Let me see if I can get this to work. Which then rises towards the surface. As it is rising, here you have a function of height and longitude. When the apex is near the surface, there are some strong retrograde flows. So as the tube is rising through the convection zone, completely ignoring the convection, the Coriolis force is acting on these flows and causing a tilt. Here you are looking at an equator on view, and this is the flux tube as it's risen to the surface. So you see that it has this tilt angle. So this explains Joy's law very nicely. More recently, since we have had monitoring missions of the surface magnetic field, we have been able to capture the very beginning of the emergence process of an active region. And what we found that is, on average, active regions emerge east-west aligned. So here you are looking at the position of the leading polarity and the position of the following polarity as a function of time, for a few hundred active regions. This is the average location. The active region, the polarities start off close together and they move further apart, and Joy's law sets in. We also found that the latitudinal dependence is only in the Y separation, the north-south separation. The east-west separation is purely dependent on flux. A large flux active region is more separated than a lower flux active region. So Joy's law sets in during the emergence process, and the emergence process is thought to be associated with the supergranulation scale flows. I should also mention that in this talk, we are only dealing with the Northern Hemisphere. So these are all active regions in the Northern Hemisphere. Can Joy's law, as an alternative, be explained by the Coriolis force acting on near surface flows? We modeled this effect using the Murem code to numerically solve the MHD equations in the near surface of the sun. So we have a box which is 15 megameters below the surface, 1 megameter above, and 96 in each horizontal direction. We have added the effect of the Coriolis force in the F-plane approximation. So it only operates on the flows in the horizontal direction. We are ignoring the vertical flows. And this is an okay approximation in the sun. You will also notice that we've increased the rotation rate of the sun. We want to have a measurable effect in the simulation time that we can compute. So we ran the simulations for about 16 hours in total, and we're modeling the rotation rate of 100 times the sun. And the Coriolis acceleration appears in the momentum equation and the energy equation. We took the horizontal velocities at the surface of the simulation. We filtered them for 15 to 25 megameters. So these are the supergranulation scales that we can model in our box, which has a limited depth and size. We've selected this scale, we compute the divergence, and we identify supergranules, which are indicated here as regions of strong diverging flows. If we average over the center of all of these supergranules we have identified, we get an average supergranule. So the white shows the diverging flows and the black shows converging flows. The cyan arrows on top show the direction of the flows. And so you see this beautiful diverging flow, similar to what you would see on the sun. So this is for no rotation. Nice. If we add 100 times rotation, you see, we can visually see it. It's easily measurable, this vortical flow that you get in an average supergranule. So you can imagine what this would look like if it was only 10 times the rotation or 1 times the rotation, and the reason we're using 100. And we'd like to understand how a flux tube interacts with the force. So we're placing a flux tube at about 11 megameters below the surface. It has a peak magnetic field value of 50 kilogauss, and it has a flux of about 10 to the 21 Maxwells, which is barely an active region, but a very small active region. We found that we had to decrease the density at the center and increase it on either side to get it to rise in that apex structure. So we have, otherwise it would rise as a full body. So we've had to change that a little bit. And we placed it in a pre-computed convective simulation, and this is a cut through that with depth and X direction here. So you can see the upflows in red and the downflows in blue. So this is our initial condition. Here you are looking at the first frame of the simulation. Here you will see the surface magnetic field, the radial field. Here you'll see the intensity. Here's the flux tube, and here are the flows. So you'll see the flux tube rise. You will see the magnetic field at the surface. We get a general bipolar structure where you see most positive field on one side, most negative field on the other. In the intensity, you will see some darkening where some concentrations of field form. So this is by no means a fully formed convincing active region, but you see the bipole structure and you see some darkening at the surface. This is a plot of the surface flux as a function of time. I've indicated 6 hours here as an approximate time when most of the flux has emerged. So you can see that this emergence takes about 2 hours. This is far too fast for the sun. We don't see active regions emerge as quickly. And we see that it forms only a weak bipole structure. So if we average over this emergence time, we can see again the bipolar structure, mostly positive, mostly negative, and we see these enormous outflows at the surface. There's a strong horizontal divergence. I want to be clear, this is absolutely not observed on the sun. We see scales on the order of the convection. So we are rising far too quickly. We're pushing the mass out of the way as we come through as the flux tube comes through the surface. So with 100 times the solar rotation, we see again the general bipolar characteristics, mostly positive, mostly negative. You would have noticed that it emerged already tilted. And the flux is more fragmented. We don't get these kind of coherent features as clearly in the intensity. But there are a few that form here. Again, looking at the flux as a function of time, in this case, it's the red curve. We see that less flux emerges, but it's not substantially different. But again, the emergence is far too quick. We'll look at the average. The bipolar structure is there. The tilt angle of that is very clear. And you can see these vortical motion from that outflow that we saw without rotation. The Coriolis force is acting on it, and we see the vortical flows. So again, strong emphasis on this is in direct contradiction with observations. This is not what's happening on the sun. We can measure the tilt angle as a function of time. Here is showing 3 frames. The crosses indicate the flux-weighted position of the positive and negative polarity. So you can see that they start off close together and they move further apart. I don't think that's particularly controversial there. And for the rotation case, we see an inclination. They move further apart, and the inclination changes a little bit. So here we see how it evolves. This is the tilt angle. We define it positive in the sense of Joy's law in the northern hemisphere. So for the simulation with rotation, it's positive. It's in the sense of Joy's law, just like we saw. Over the emergence time, it emerges around 30 degrees, and this increases as a function of time. For the case without rotation, there is some drift here. It emerges pretty much east-west aligned, and we see some drift. So in both cases, the tilt angle changes as a function of time. So now let's scale it back. The rotation on the sun is about 100 times less. The surface velocities are about 70 meters per second, as opposed to 2 kilometers per second, which we have here, because our flux tube is rising too fast. The emergence time takes about 2 days, compared to 2 hours. So if we do a little scaling exercise, we know that it's the delta Y component that is dependent on the Coriolis force, as opposed to the east-west, which is dominated by the flux. We can do a scaling exercise to expect what we would get for the sun, and we get about 8 degrees, which is on the order of Joy's law that we observe. A second test we did was we computed the indirect tilt angle. So we are computing the displacement expected from the flows acting on the magnetic field. So we're taking a cumulative integral of the flows weighted by the magnetic field. It's like a mask. We get the separation in the east-west direction, the separation in the north-south direction, and we can compute what I call the indirect tilt angle. It's dependent on the flows. The indirect tilt angle is shown by the dashed curve. And so you see here, it follows very closely. In the case with rotation, the same trend is followed. During the emergence, they are the same. And this offset is due to the more dispersed nature of the flux at the surface. It's more spread out and captures different components of the field, of the flow. So this suggests that the tilt angle is entirely consistent with the polarities being buffeted by the surface flows during the emergence. So this Coriolis force is pushing them around So we definitely need to explore higher flux, more stable, structured active regions, and absolutely with a slower rise speed. But the scaling indicates that this is consistent with what we would expect in the solar case. Having said that, all active regions begin as small, weak bipoles. So we have captured that component of the emergence. For me, what would be interesting to see next is how Joy's law may be generated in global simulations where the flux tubes are generated within the convection itself, and see if this is consistent. And of course, we should take a closer look at the observational flows. So thank you very much for your attention. Yeah, I'd be happy to answer any questions.
Okay, thank you. Gustavo?
Thank you, Hannah. I am Gustavo. So my question is, why do you have to go to 100 solar rotations and you don't have one solar rotation and you see what happens?
You cannot see it in one solar rotation. You would need to average over hundreds and hundreds and hundreds of emergences to average out the convection. So we need to turn it up to 100 to get it above the convective signal for one. If we could do many simulations, no problem.
Right, Divyenu here. So typically you'd expect to see a dependence on flux on the tilt angle, which you also talked about. Did you manage to do some rounds to see if the near surface Coriolis force effect could actually reproduce that particular result, the scaling?
So two things. In my observational work, I haven't seen it dependent on flux yet. Secondly, we found it was a trade-off in creating these flux tubes. If you wanted a higher flux, it would then have to be wider and not as deep, or you can keep it narrow and increase the amplitude of the field, which would then also decrease the density and make it rise even faster. So there was these funny things we had to sort of balance out there. So we have not done a study with flux, no.
Thanks.
Okay, more questions? Alexey Pevtsov.
Thank you. So in observations, you see indication that tilt actually decreases at certain latitude. So it's almost like a peak at certain latitude, and there is a decrease. Do you see anything in your data?
We haven't done it for different latitudes, and so I think that result comes from sort of a static look at any active region that's on the surface rather than as a function of lifetime either. And so we're focusing here on the lifetime. We've done it for one latitude, which is, we chose 15 degrees, but when you're rotating it 100 times, the solar rotation rate doesn't really matter. So I haven't seen that, no.
Irin Kitiashvili, very interesting results. And I have a question about your kind of setup and how it reflects in the results. So my understanding, maybe I'm wrong, what you don't introduce twisting in your flux tube. And
no,
and my question is, if you do or not, but how a twist of flux tube will interact with Coriolis force?
Wonderful question. This is exactly what might help it stay together as it rises. We have got no twist in our flux tube at all. We wanted it to be as simple as possible, not to sort of confuse that issue, because that is the other option for what could be driving Joy's law. Yes.
Okay, Amy Norton.
Hi, thanks for the talk. Two quick questions. So you said there was an 8-degree Joy's law, but both plots I saw were 30.
Yes, so we scaled the north-south separation by reducing the number by 170 meters per second on 2 kilometers per second and the emergence time to get an estimate if we scaled all these things back to the sun.
Okay, and you didn't have a plot versus time for that. It was just an estimate.
It's just an estimate.
Okay,
yeah.
And then the other one is, how hard would it be to push through a omega structure from the bottom boundary already instead of a flat?
Yes. So there are some beautiful active regions that are formed by pushing something through the bottom boundary. I was inspired, or we were inspired by these simulations by Hotter et al., where the tube was placed and it rose very nicely and formed one. And we wanted to reduce the in position as much as possible on the structure. But maybe that is something we have to do in this case.
Okay, Matthias Rempel.
Very nice work. I had this impression from your observations that when the active regions emerge, that first there is no tilt angle really visible, but in the simulation, it starts right away.
Yes.
With the tilt.
So if we scale that back, so yes, so as the flux tube is rising through the convection, it is creating enormous horizontal outflows the whole way up. And so the near surface flows can generate that tilt angle, is our conclusion. And there could be, at least at the surface, there could be a tilt angle when it emerges.
Okay, more questions? I have a question. You have such strong rotation convection. Probably you have also local dynamo effect here.
I have not explored this option.
No local dynamo?
I haven't checked, haven't looked. The horizontal flows are the strongest. So there is the vortice, and you can see in the movies, the ones that get caught in the downflows are spinning around there. But there is no significant generation of new magnetic field.
Interesting. Okay.
So you used a scaling argument to try to reproduce the tilt angle observed for the sun. Do you have an estimate of basically how fast does a star have to be rotating for that tilt to be significant at all?
Sorry, ask that again. What tilt to be significant? For what?
So at what rotation rate, presumably below the solar value, but is that estimated tilt angle significantly non-zero?
Right. So if we're rotating at the rotation rate of the sun, the effect of the Coriolis force is very close to the buffeting of the convection itself. So we have that tilt angle, and they're sort of not in competition, but they're working together, and they're of similar amplitude, which makes it so difficult to measure that. I do not have a number for you, but at the sun, we're on the order of that they are compatible.
Okay, thank you. No more questions. Okay, thank you very much. So now we have brief presentations of tomorrow's posters. So now you can see a list of poster presentations, so please come here. And again, you have, as brief as possible, we have only 25 minutes, all of them. So please just end.
Should I start? Okay.
Yeah, please start here.
Hello everyone, I'm Shaunita from IISER Kolkata. So my poster is based on our recent published work titled as Algebraic Quantification of the Sun's Dipole Moment, Probing the Role of the Babcock-Litton Mechanism in Solar Activity. So the motivation of this work is based on reconstruction of the dipole moment of the sun, which can act as the precursor of forecasting the upcoming solar cycles. Now, calculating the dipole moment can be done in many ways. We mostly use different type of numerical models like the solar dynamo models or the solar surface flux transport models. But in this type of numerical models, it involves various free parameters for which sometimes the calibration process becomes lengthy and tiresome. So what if we took up this type of computer intensive modeling and just implement some simplified analytic approach for calculating the sun's dipole moment? So this is what we exactly did in our work. Well, so we use the observed data, we drive it to a purely analytical model to reconstruct the dipole moment of the sun over past century. We found that our observation matches, our reconstruction matches well with the observed data. Also using this reconstructed dipole moment, we can post-predict the solar cycle amplitudes of the sun for over past century, and also predict the amplitude of solar cycle 25. We found that solar cycle 25 would be as strong as solar cycle 20. So to know more about my work, the data, the methodology, and the results, please come and visit at my poster, which will be, the session is tomorrow, and it will be screened in screen number 49 for morning session and 60 for the afternoon session. So I would be happy to discuss with you and having those suggestions. Thank you so much.
Thank you. Okay, my name is Alexander Kasovichev, and in our poster with Valery Pipin and Alexander Getling and Krishan Mandal, we present some results on how we can use helioseismology to test dynamo models. In particular, using data from Soha and TDO mission, we measured variations in internal flows over 2 solar cycles. And these variations, they show some kind of migration pattern that looks like dynamo waves. And also develop a solar model, dynamo model. And these actually patterns reproduce qualitatively very well. So and this dynamo model is a Parker type dynamo model. So we can see there's unambiguous evidence of Parker dynamo waves inside the sun. In addition, this dynamo model predicts variations of over what's called extended solar cycle that observes in torsion oscillations, also in meridian circulation. And what's interesting, that variations in meridian circulation are found even there is no magnetic field on the surface of the sun. So it's completely driven by the internal dynamo effects. So it also this model includes emerging active regions, and so please look at this poster.
Hi, my name is Rajaguru. I am from the Indian Institute of Astrophysics in Bangalore. So this is a work which I've been doing with the team at Stanford, as well as the HMI team, as well as the GONG team, which is in Boulder. So this is a part of a larger project, which Ruizu will talk next. So this is for studying the meridional flow as part of this big project. I have been looking at the cross-equatorial flow, which is already known. So the plot here, sorry, is there a pointer? Oh, here. So here, what is plotted here as a function of time, the cross-equator average over -10 south to +10 north. The flows, meridional flow averaged, and the color scale blue is southward. So when it is red, it is, when it is red, it is southward. As a function of time, and the curve which is shown, the black curve, is the north-south asymmetry in the magnetic field. There are two things. The cross-equator flow itself is known, but what we show here is that the cross-equator flow forms as a local circulation. As you can see, the red turns into blue across the equator. It goes in depth, the y-axis is depth. The sign change in the flow, the return flow happens just below 0.97. It's about 15 to 20 megameters. So we measured both in GONG and HMI. It's a clear detection of local circulation across the equator. It is driven by the active regions. So the active regions have a large scale inflow. So when there is an asymmetry in the magnetic field, here in this case, the southern hemisphere was much more active. There are more sunspots in the southern hemisphere than in the north. So that drives the flow across the equator. So that's the one result. And then, so as a function of cycle, this is as you can see, we also included some data covering the current cycle up to 23. We don't see such a large cross-equator flow in the current cycle. That's because the sunspots in the north and south are more or less symmetric. All right, so that is quickly. So the one other thing which we compared was this: a plot which shows the changes in the meridional flow as a function of latitude versus time diagram. Here is the logarithmic gradient of rotation rate and how it changes over time. These are changes in the gradient of rotation rate. This is from global seismology. As you can see, in the active region, when there is activity, there is a larger gradient. So the gradient itself is negative. So when it is blue, which is negative, means the gradient is larger near the surface. So this is near the surface, and we just compared this as a function of depth, how this gradient as a function of time over depth compares. So as you can see, the inflows has a good close correspondence with the rotation rate change. The depth at which they both change sign are almost the same. So this we believe is, if you want to know more about it, you can come and talk to me. My poster is number 23 tomorrow. So thank you. Thank you.
Oh, thank you. Oh, that's your summaries. Okay, Ruijo.
Hello, this is Ruiju Chen from Stanford University, and I'm talk briefly about meridional circulation measurements. Okay, so as is known, the meridional circulation is very important for understanding solar dynamo and dynamics. However, multiple measurements among different methods are only consistent from surface to about 0.9 solar radius, which is a shallow poleward flow. But beyond that, some results have reported a shallow return flow that is equatorward, but others only see the return flow at bottom of convection zone. And then in even deeper regions, some see a poleward flow again at bottom of convection zone, while others see equatorward. So these forms different overall circulation pattern. These are like typical double cell circulation pattern, and these are like a one cell one. So why is it so difficult? The challenge is like one, the deep flow signal are so small that they are 1 order of magnitude smaller than the systematic effects. And second, the multiple authors' measurements are, although following the same method and procedure, they have subtle differences in every procedure in the actual analysis. So here, the purpose of this study is that we gather the authors of previous study that can do independent measurements of meridional flow. And we actually have 4 authors here. We do a step-by-step comparison on both HMI and GAN data for over a solar cycle. So we do a comprehensive examination to find where does the discrepancies come from. And okay, go to my poster to see more details. And the main conclusion here is after reconciling the data and data preparation, and when comparing the exact same thing, we see no discrepancies. And also, although we do find some differences in the systematic effects in HMI and GAN, particular north-south offset, go to my poster to talk about more details. Screen number 20. Okay.
Thank you.
Hi, I'm Amy Norton, and I'm here because Todd Hoeksema could not attend, unfortunately, the meeting. And his poster, which will be shown tomorrow, is basically an advertisement for the effort of COFFEES, which is a NASA Drive Center. NASA Drive Centers were recommended in the 2013 detail survey for establishment of a very large amount of people in multiple institutions to tackle a project with a breadth that's larger than a single research group could tackle. So it's hosted through Stanford, and Todd Hoeksema is the PI. And we're basically a very large group with 11 institutions looking at multiple aspects of the solar dynamo and how the sun operates in the interior. And we have expertise in helioseismology, dynamo modeling, surface magnetic fields, et cetera, et cetera. And many of us here are COFFEE members, Sasha, Irina, Gustavo, Reju. And so basically we have open seminars and discussions which any of you could join. Just go to the coffees.stanford.edu website if you'd like to follow along and have more meetings on your calendar than you already do. And that's all.
Thank you. So I'd like to urge that everybody who wants to join this, please contact Amy or me. Okay, so this last one, so it's, I don't know if it's, the author is here, is this online? Okay, this is about L4 mission, so it's very important poster. So please look also at Dr. Han is not probably here, not online. Okay, so this is end of our second session. So we have 15 more minutes for posters. Please look at posters. It's the last chance to see today's posters, okay? And if you present a poster, please stand near your screen. Okay, thank you. So we reconvene at 3:30. Svetlana, you're online?
Yes, I am online.
Yeah, please connect online. Yeah.
But it shows me I cannot start screen share. Yeah, now.
Yeah, we can see you.
Okay.
You can share your screen, I believe.
Share. Open. Yeah. Should I?
We don't see your presentation. Please.
Yeah, wait a second.
Sure.
Oh. Can you hear me?
We can hear you, we see you, but we don't see your presentation.
I don't know why.
Share presentation. Yeah, please just open the presentation and share screen. Yeah, we still don't see your presentation. Yeah. What? Okay, now as you can see your presentation.
Oh.
Okay, thank you.
Okay, thanks for waiting.
Okay,
But,
now that
yeah,
still, yeah, so, okay. So that the first talk now at this session is Svetlana Hubrik, magnetic field of massive stars. Okay, please, Svetlana, you can start.
Okay, good afternoon. So I will speak in my presentation about what we know now about magnetic fields in massive stars, and first about magnetic field generation, which scenario exists currently exists, the role of magnetic fields in massive stars, and about surveys which have been carried out in the last years. And then what we measure in massive stars with different designations and kinematic characteristics, and also mention the future studies. Okay, 22 years ago, we did not know that massive stars have magnetic fields. So the first detection was in 2002 by Donati et al. And then, yeah, for the time being, we have more than a dozen known massive magnetic stars. But what we see in this list that there are 5 OF question mark P stars And there are in our galaxy only 5 such stars, and all of them have magnetic fields, but only 5 have been identified by Nolan Balbon, and all of them have large-scale organized global magnetic fields, most of them of kilogauss order. So now we know that magnetic fields are present in stars across Hertzsprung-Russell diagram, but what we need to know, of course, the consequences of their fields for the further evolution and their final fate as supernova and compact object. And of course, the most persisting question is how such magnetic fields are generated. And there are different scenarios have been suggested. And so, for instance, fossil relics from star-forming molecular clouds, then dynamo in convective cause was suggested. Now, most popular scenarios are strong binary interaction during mass transfer or common envelope evolution, or stellar mergers during pre-main sequence stage or early on the main sequence. According to Ferrario in 2000 et al. In 2009, the merger event should take place early enough in the pre-main sequence stage. And also, Tokovinen and Moore have presented a toy model which predicts a large number of mergers, and owing to strong accretion and consequently fast migration in the dense environment. Now, what is the difference between magnetic field origin, also what we call fossil fields, and dynamo fields? Of course, fossil fields are largely organized and long-lived and stable, resisting ohmic decay, combination of poloidal and toroidal fields, and they are observed in these fields. We call them fossils, but of course, yeah, it is maybe because we are not sure when they are organized and how they are organized is in a magnetic field, and found in radioactive OBA stars. And dynamo fields have, of course, a complex structure and permanently regenerated with flips, and found in convective type stars, and they need differential rotation and micro Gaussian fields. The role of magnetic fields in massive stars, of course, we know. The suggestion that, for instance, magnetars, the progenitors should be massive O-type stars. Then they have, of course, on the evolution of massive stars, also supernova, some kind of supernova. They have effect on rotation. We know that many of them rotate pretty slow. And although on the structure, dynamics and heating of radiative winds, and with wind plasma confined in dynamical and centrifugal magnetospheres. But also what we discovered in the last year, it's also magnetic field causes element stratification. For instance, we tried to measure magnetic field and using a different line list. And here on the right side, I show the plot where the measurements show that using helium lines, the strength of magnetic field is much lower than using oxygen and silicon lines. At the bottom, I show some simulation with Nirvana code, which was created in our institute in Potsdam, of one typical magnetic O-type star, HD 50879, and for 2 different strengths of the field, 200 Gauss and 2 kilogauss. And we see that much more gas is trapped for the fields with stronger field. There is also more gas, and but this calculation are not 3D, these are 2D, and there are some assumption like axis symmetry, non-rotating, which maybe can be assumed if stellar rotation is very slow, and isothermal, which is also not a good thing. And just about magnetospheres, The impact of the stellar magnetic fields on the wind is described by the confinement parameter and eta. And in this formula, you see that B equator, magnetic field strength at the equator, then stellar radius, and m dot is the mass force and terminal speed. And for instance, for this star, which we studied now already for almost 10 years with dipolar strength of 2 kilogauss, Alphen radius is 11.7 stellar radius, and a Kepler rotation radius of 313 radius. So that this star possesses a dynamical magnetosphere. On the right, I show the difference, what we call centrifugal magnetosphere. Then if Alphen radius is much larger than Kepler rotation radius, and dynamic is vice versa. And since the star was so much studied, we found the rotation period, it is very long, it is 7.41 years. And this is from longitudinal magnetic field measurements. This rotation period was derived, but also H alpha profile variability is, also shows this the variability with the rotation period. So we just use dynamic spectrum to show the variation, and the strongest emission is here highlighted by red color, and we observe the strongest alpha emission at the phase when the magnetic negative pole is best visible. On the left side, these are just in the last year what we recorded with H alpha, and then over the 10 years. But other stars, they have also H alpha variation, but for this star, because it has very, very narrow lines due to very slow rotation, you see a very nice structure showing the magnetosphere around this star, dynamical magnetosphere. There have been a number of collaborations working on the detection of magnetic fields. It started with Marjorie using force tube, and then Mimas using also actually all known spectral polarimeters, 4-meter class telescope, and force at the 8-meter telescope. And what is important, the observation have been carried out for 150 OB-type stars and clusters in the field. And for probable cluster members, and we also checked the membership and checked the kinematic photometric probability, and also found out that a number of studied stars have a runaway status. But the evolution of binary and multiple systems with magnetic components has not been explored until now. In the list, what I showed with now known magnetic stars or type stars, there is only one star, Plaskett star, with very short orbital period. It is not very short, but it is around 14 days. But all other stars appear either single or are in very wide binaries. And in agreement with this scenario merger interaction, which is now very popular, we recently showed or published last year that numerous components in binary multiple systems possess detectable magnetic fields. Of course, the measurements of multiple systems is much more difficult because all the stars have different masses, and you work with completely different line list trying to detect magnetic field. We studied 36 systems and definitely detect Zeeman feature in Stokes V spectra have been found in 22 systems. It does not mean that all 22 systems are really magnetic, because there could be also background or foreground targets also magnetic, but for some stars we are pretty sure that the signal comes, magnetic signal comes from this object. And what's also interesting that our survey included system at very different evolutionary stage. We had also very young main signal systems in the Wolf system, in the Wolf system, and these blue supergiants, Wolf-Rayet stars, and one system with luminous blue variable candidates, one post-supernova X-ray binary. Here I show a few examples, discoveries of magnetic fields, and for some of them we obtained now observations with half spectral polarimeter on last year, and could also confirm the presence of magnetic fields. Here on the left side, so these are LSD measurements. LSD, least square deconvolution. So it means that we use a number of lines to increase the signal to noise, because of course massive stars have so few suitable spectral lines, so it is better to work with a number of them. And many stars where we also detect Zeeman features are classified as X-rays, colliding wind binaries. We have also a number of triple system, one triple system, 167, 794. I cannot read because I see myself there. And this classified as particle accelerating colliding wind eclipsing binary with blue supergiant, also PRCV, also the names. And the new observations hubs now from June show that they also show Zeeman feature. In these plots, in the middle, we show Stokes-V spectra, so in the bottom are integral line profiles, where you see that all the system are multiple, as a binary or multiple, and we see the correspondence of Zeeman features in the Stokes-V spectra to some of the components. And the upper spectra, these are what we call diagnostic null spectra, that observations are combined of polarized spectra in the way that there should be no signal. So it is like a check for the validity of the detection. So, and we also could confirm also the presence of magnetic fields in some other binary system. So on the left side, these are old observations of 2008 or whatever, and the new observations also show the presence of magnetic field. One system we wanted to already observe for a long time, since Mai et al. Published a paper on the triple system 150 to 136. And because they also showed the position of components in Hertzsprung-Russell diagram, and one the primary component, which is more massive, is less evolved, and this of course indicates that there should have been a mass transfer in the system and then renovating the primary. And indeed we could, the weather was not so good now in June, but we managed to get one observations, and we also detect that the primary is magnetic. So it is good thing to know where the components are located in the Hertzsprung-Russell diagram, and to see whether this component possess magnetic field. Another class of O-type stars, so-called strip stars, where the envelope is already lost. The best example for such stars sind Wolf-Rayet stars, but of course they have very strong winds, and the measurements are very difficult because we see only winds. But already for two stars, the measurements have been reported where it was possible. These are not Wolf-Rayet stars. One is B star, the Sagittarius, with rather low magnetic field strength, only 70, 80 Gauss. You see with blue, we highlight the Zeeman features. And last year, Shina et al. Detected very strong magnetic field in quasi-Wolf-Rayet binary, but it is not Wolf-Rayet. It is called quasi-Wolf-Rayet because it has strong emission lines, and it shows 13.5 kilogauss field. And now we, in October last year, remeasured magnetic fields now, and field is variable, so we measured minus 1.5 kilogauss using force observations. And this is, of course, detection for such stars is very important because it gives us clues on the origin of gravitation wave sources, luminous X-ray sources, and also stripped envelope supernova. And now we also, for the first time, also detect magnetic fields, extragalactic and massive stars. And the idea is that there are only 5 galactic OFP stars, but there are 6 in the Magellanic Clouds, in the small and large. And because they are very similar, this, of course, you expect that maybe they also have magnetic fields. And but these stars, of course, in other galaxies, we need low resolution spectroperimeter at the 8-meter telescope. So we used FORCE in October last year. We managed to observe 4 OFP stars and 1 massive contact binary to understand also how the interaction plays a role. And we found actually kilogauss scale magnetic fields in 2 OFP type stars and also in the contact binary. And this was the first detection, extragalactic detection, and also in the low metallicity environment. And it shows that the occurrence and strength of magnetic fields in also in low metallicity is similar, maybe similar to our galaxy. And the plot here above in the figure I show above, this is simulation presented by Schneider et al. For the PEGE event. And below this is Fobe model of the contact binary in the small Magellanic Clouds, and then observations with FORCE, where you see the integral spectrum and Stokes V and N spectrum. And magnetic field is detected using a regression analysis. And now outlook, of course, we had for the 36 studied systems, there have been only snapshots. There have been in the archive only 1 or 2 observations, and those that for most promising candidates, we need to do a monitoring. So we continue monitoring and search for magnetic fields and contact over contact systems and system with stripped components, and also systems at different evolutionary stage. And one of the next steps, it would be interesting to observe magnetic fields in blue supergiants. We had some blue supergiants in our sample, but it would be, of course, better to have a dedicated observing campaign. And the problem is that there are too many observing the Helption gap. I show here the picture from the paper of Burgess et al., where they show the position of galactic blue supergiants. These are stars with the spectral type B, null B1. And since, though you don't expect so many in this in this gap, they call this overdensity, and as a scenario, it was suggested that the stars are stellar merger. No, thank you for your attention.
Much.
Yeah.
I'll take questions. I have a question that what the mechanism, we mentioned the dynamo mechanism in these stars, it's they're not convective, so it's not alpha omega. Is it magnetic rotation stability or tidal effects, tidal dynamo? What kind of dynamo works?
Although the idea is that there is interaction when we have a mass transfer in multiple systems, that we get also some kind of differential rotation. And if we have already some seed field, even small, though one can still get stronger fields and so on. Yeah. And this idea with merger is also interesting because all people say, okay, there's a merger among O-type stars. There was all the paper from De Mink et al. And telling that about 8% or 9% could be merger. And then before we looked at the binaries and multiple systems, people always said, so this is more or less what De Mink et al. Suggested. But the problem is that there's a frequency, the occurrence of triple systems, of a quadruple system of triple is 35% among O-type stars, and quadruple even more, 38%. And so they are much more frequent than single or binary stars. And now the theoretical consideration with some code or multiple stellar evolution code shows that among these multiple systems, at least 70% of them undergo a merger event during their evolution. So actually, we should expect maybe 20-25% at least merger product. And they will be later talk of Frost et al., which also discuss the presence of magnetic field in one binary system, where they suggest that one of them is a merger product.
Okay, thank you very much. Okay, we don't have more questions. Okay, thank you. Thank you, Svetlana.
You're welcome.
Okay, the next speaker is Gustavo Guerrero about 3D MHD simulations.
Hello, everyone. Good afternoon. So I will be speaking about 3D MHD modeling of solar and stellar dynamos. And this is a very broad topic, as we saw the last presentation. So we have magnetic fields in kind of every star. So I will be talking only about convective stars and the ones that are more similar to our sun. I do work in Brazil, the Federal University of Minas Gerais, and I belong also to the COFIS collaboration. What I will present today, you can find in this review paper published last year. So let's start. This is what we need to reproduce. These are the relevant solar and stellar observations. For the sun, we know pretty well the solar differential rotation, and we know how it goes with depth. We know that there is a tachocline, and that below the tachocline, the rotation is like a solid body. And then we have the magnetic field, but this magnetic field is at surface level. So we should not rely too much on this, because this is what we observe, and we have information from the depth. So we have a gradient of temperature, and we have a gradient of density. And so we have, as the weather on Earth, we have functions or balanced states that rely on these gradients. So this may be only a manifestation of the magnetic field below the surface. And we need to know how these flows here are generated, and why they have the form that they have. Look at this, these are tilted. And there is a layer of radial shear at the base of the convection zone, and we need to understand why do we have this tachocline. And we have also a radial shear close to the surface. We still need to understand why do we have this layer. And regarding magnetic fields, we need to know where is the dynamo that is generating this pattern at the surface is located. It is at the base of the convection zone, at the tachocline. It is distributed in the convection zone, or it is seated just close to the surface. There are dynamo models working in all these possibilities. We also don't know how the sunspots form. These are buoyant structures that come from the bottom of the convection zone, or they form close to the surface because of magnetic field instabilities. All these possibilities have been studied also. What about stellar magnetic fields? For this, we have some information also. The main information that we have is that there are two regimes for the amplitude of the magnetic field, or the magnetic field intensity, that can be measured with proxies like X-ray luminosity, or can be measured straight with magnetic fields. And we have a region where the magnetic field grows with the rotation, and then somehow it gets saturated. We have a saturated phase also in this diagram as a function of rotation. So the faster rotating stars, they have a magnetic field amplitude that is more or less constant. So how come we have this? There are two different kind of dynamos operating in different kind of stars. And when we go to see the cycles, the evidence until a few years ago showed that yes, maybe we have different kind of dynamos operating, because we have, for the active stars, we have one branch, and for the inactive stars, we have another branch in terms of cycle of rotation and cycle of the period. But very recently, Alfio Bonanno and Corsaro just explained this dichotomy in terms of the stellar metallicity. Alfio will speak about this tomorrow, so I will not say anything else about this. But these are the kind of things that we need to reproduce with global 3D MHD simulations, and I go to the end of my talk. We don't reproduce this, unfortunately. So what are the equations that we have to solve? I will go a little bit fast here. We need to solve the MHD equations. So we have conservation of mass, of momentum, of energy, and we need to conserve also the magnetic flux. So we have to solve the induction equation. And for the 3D global simulations, we do this in a sphere, considering some fraction of the solar radius. Some simulations go deeper, some simulations go from the convection zone of the sun only. And of course, this domain can change depending on the star that we are interested in simulate. And of course, there are simulations, or there are stars better, that they don't have convection, or the convection zone is just below, inside the surface. And for this kind of stable stars, the kind of dynamos that can be operating are different than the things that I will show in this talk. But Laurin will speak tomorrow about magnetic field in stable layers. So if we want to convert these equations into non-dimensional form, we get some non-dimensional numbers, and these are just comparisons with different time scales happening in the simulation domain. Like the Rayleigh number is a comparison between the buoyancy force and the diffusive forces that are inside the domain. We have Prandtl number, or Taylor number, and also the Coriolis number, that is a comparison between the advection and the rotation of the star. And this is a Kolmogorov turbulence diagram. If we need to have a simulation covering all the possible scales, then we go from the injection scale. Here is the wave number, so here is the larger scale, and maybe we have some injection of energy at this scale, and then this energy decays toward the dissipative range, and then all the energy dissipates at very, very small scales at the molecular level. And the energy decays following the Kolmogorov rule, but we can also have inverse cascade contribution from the smaller scales towards the larger scales. And that is what happens in dynamos, where the small scale turbulence amplifies large scale magnetic field. And we cannot get DNS in simulations. It's very expensive computationally. But it's possible to get some information from the unresolved scales and plug this information in these MHD equations, and then we have some large eddy simulations or implicit large eddy simulation. And this is basically what all the groups working in global simulations of the sun and these kind of stars are doing, okay? So these are the third option here. The mean field model is only working in the M = 0 mode. And this is what is called mean field simulation. And the problem with this is that there are several free parameters, so the answers are ambiguous. And the Babcock-Layton mechanism is one of these models. And unfortunately for the Babcock-Layton mechanism, we don't have a mathematical formulation to add this in the mathematical equations of MHD. So Babcock-Layton mean field dynamo models are mathematically inconsistent. These are the scales. So going back here, so we need to solve all of this. These are the scales that we need to solve to have a DNS, but we cannot do this because we need a lot of computer time. So these are the parameters that I mentioned, the non-dimensional parameters. These are the values for the sun, and these are the values that we get in the simulation. So you see that the global simulations are still very far from realistic parameters, right? And regarding the temporal scales and the spatial scales, simulations just cover this kind of the spatial domain and this part of the temporal domain. So it's still a lot of work to do to get global simulations working in the full spectrum of time and spatial scales. I will show you some results from the dynamo simulations that we have, more recent results. We have global simulations since the 70s. The first works on this were did by Peter Gilman. But I will just present some of the most recent results. And the goal of these results is trying to answer the questions that I put at the beginning. So where is the dynamo located? So some of these simulations just work within the convection zone. And within the convection zone, we can get a dynamo. This is called a distributed alpha omega dynamo. It works because of the turbulence. And you see that you can have reversals even when we have very high resolution, like the simulations of the UKJ, or we can get organized reversals in lower resolution. Unfortunately, going up in resolution doesn't mean that we are going better in the simulations results. And also we can get from the simulation the mean field flows. So we have the differential rotation, and to get accelerated pole, we need to do some tricks. It's not easy to get this. I will go to this later. So it's possible to add also a stable layer below, so we can somehow reproduce tachoclines in the simulations. And when we add the tachoclines, we have stable magnetic fields, and we have cycles that are longer than the cycles that we get when the simulation just cover the convection zone. And this is interesting because we know that the sun has this layer which has a strong shear, the tachocline, right? So this is simulation from Mesada and collaborators, Sasha Brun in 2022. This is with the ASH code, and this is Petri Kapila with the pencil code. This is in the so-called sphere in a box simulation. So there is a box, and the simulation is run in Cartesian coordinates, but within this box, it's possible to put a sphere inside. And then he gets these very nice results, but this migration that looks like the sun appears here at the bottom, at the upper boundary of the simulation of the sphere. And this is where the simulation is not so good, because in the sun we have several orders of magnitudes of change in density, but the simulation just have 1 order of magnitude of change in density. So it's not so clear if these results are correct in terms of comparison with the sun. And then I will show you my simulations. This is a simulation performed with the EULAG code. Some of the simulation results are presented in 2019 by myself and also Sasha Kosovichev and other collaborators. And this kind of simulation that I have here is not published yet. My student Luisa Almin is working in the analysis of this simulation, but I can just play the movie here if I manage to do this. Okay, so this is how it looks, the simulation. The magnetic field is generated at the Tacoc line. The magnetic field is stretched by rotation, but differential rotation, and then something happens. We call this alpha effect. We don't know how it works, but you can see something very weird happens, right? So we try to explain this in terms of mean field dynamo. And unfortunately, when I was trying to convert from Linux to Windows, I got this, but this is a good representation of the understanding that we have. Just kidding. We understand more or less that the toroidal field develops because of differential rotation. And the interesting thing of this simulation is that we get a magnetic alpha effect happening at the base of the convection zone. So it's a magnetic alpha effect. It's not a kinetic alpha effect. What is the reason of this magnetic alpha effect? Maybe it's Tyler instability, or maybe it's buoyancy instability, which we do have in this simulation. And the buoyancy instability in this simulation doesn't look like magnetic flux tubes, but it looks like magnetic bubbles. If you are interested to see how it looks like, you can contact me later and I will show you some movie on this. So what is important also in this work of Luisa Almingen and other students of mine is that we can compute the turbulent coefficients. My student Guilherme Monteiro merged the EULAG code with the pencil code. And now we are able to take a simulation from the EULAG code and compute the dynamo coefficients using the so-called test fit method. That is a very good way of computing the alpha effect and the turbulent magnetic diffusivity. So we are working on this in understanding what is happening, but we can see that for generating the radial magnetic field or the poloidal magnetic field, we have a strong signal that is below the convection zone. So this corroborates what I mentioned in the previous slide, that the magnetic field develops and evolves mostly at the base of the convection zone, and then there is some emergence, of course. The problems that we have to solve the magnetic field or the simulation is mostly related with the convective conundrum. We don't know pretty well how are the scales, or better, what is the power of the motions below the photosphere. This is the Dopplergram, and we can see the supergranules here. We can get the energy of the supergranules here, but we don't know how is the energy below the surface when we go to larger scales. So the recent PhD thesis of Prosauf showed that the energy for the largest scales is very, very small when compared with the simulations that we are doing. And the problem is that these simulations rely in the mixing length theory. So perhaps there is, if these results are confirmed, perhaps there is something wrong with the mean field theory, and we have to work on this. And this is also evident when we try to do stellar evolution simulations, and there is always kind of a lot of dispersion for the low mass stars where the convection occupies most of the star, right? So if you go to the work of Espada in 2013, you will see that there is always, and works later than this, show that there is a difference in radius of 3% between the stellar evolution model and the observation of radius of this kind of stars. So because of this, we have simulations where if we put the solar luminosity and the solar differential rotation, we get a slower equator and faster pole. And if we then do some tricks like increasing the rotation or decreasing the luminosity or increasing the thermal conductivity by a lot, several orders of magnitude, then we can artificially decrease the convective velocity, and then we can get the solar differential rotation. But this is doing kind of by hand. It's a trick. Yeah, I am almost finishing. Something that is very exciting and is recent is that we are observing Rossby modes, and we have the equatorial Rossby modes, and we have the high latitude modes, and this has been explained very nicely by hydrodynamic simulations by Laurent Guisson, and Yuto Becky presented a very nice talk yesterday. And I am also working with this with my former student Marianne Diaz, and these are global simulations with OILAG, where we force, as a body force, the solar differential rotation, and we basically obtain all the observed modes. So very interestingly, from the work of Yuto Becky, is that we know now why or what are these modes doing. So they are very relevant to determine the differential rotation and also the transport of heat from the equator to the pole or vice versa. So these are simulations performed by Marianne. Here we have a 20% shear between equator and pole, and this is 40% shear. And you see that the results are quite different, but we get a very nice polar vortex, which is similar to what we observe in the sun. So what do we learn from this simulation? We learn the origin of the Rossby modes, and the origin is shear instabilities at the tachocline. At the small scales is Kelvin-Helmholtz instability, and larger scales is baroclinic instability, as was presented early by Ziembowski and Kosovichev in the 70s. We know that for the largest shear, we have the larger energy in the unstable modes. And for this case, we still can have secondary instabilities. And you can see that there is a m=1 very, very strong mode for this case. So perhaps these active longitudes appear because of Rossby or inertial modes operating inside the stars. The modes are 3D, as you see in these simulations. So we start in a domain that is three-dimensional, goes from the radiative zone all the way to the surface, and you can see that the modes propagate radially. And finally, these modes contribute to the transport of angular momentum and to the transport of heat. So to conclude, oh, by the way, yesterday I mentioned that these modes, especially the polar vortex mode, was observed deep down till 0.4. This is the work of Krishnendu Mandal and Hanasoge. But in the published version of this work, they only mentioned that this goes deep down till 0.6. But in the archive, you can find the previous version, it goes till 0.4. So what is this mode doing to deep down till 0.4? I really don't know. Conclusions: global simulations have substantially evolved since the seminal works of Peter Gilman. Recent models include most of the necessary physics, but they don't have sufficient resolution to model the complex system with high Reynolds number and high magnetic Reynolds number. For today's supercomputing, performing DNS is unfeasible. Subgrid scale models are required to improve the modeling. And you mentioned yesterday that it's possible to do when we know a few physics and we need to know more physics, we can do machine learning and combine it with physics simulations, with MHD simulations. And this can represent a very good opportunity to get, with machine learning, what we don't understand from turbulence. Most importantly, we need to understand the physics of solar and stellar structure, possibly solving the convective conundrum. And Rossby waves are a remarkable opportunity to understand stellar interiors. The role of magnetism in these Rossby modes is still to be explored. Mausumi Dikpati has some recent works on this, and there will be more in the future. Thank you very much. Questions?
Okay. Christoph Petrov, I have two questions. First is you conspicuously skipped mentioning the hyperdiffusivity techniques, so I would be interested to hear your opinion. And the other question is that given that the thermal timescale in the deep interior of the sun is 100 million years or something like that, how do you consistently develop the tachocline?
Yeah, these are great questions. So for the tachocline, this is not self-consistently so far, but I can get a tachocline that dissipates in a very, very long time scale. And for your first question, some simulations use hyperdiffusivity, some simulations use explicit diffusivity, regular one, and some simulations use implicit diffusivity, so they don't use any explicit diffusion term, not for viscosity, not for magnetic fields. And this is what these simulations are called implicit large eddy simulations. And some of them use, I don't personally use hyperdiffusion, but this is a way, of course, to increase the Rossby number artificially.
This is Yuto Beki. Thank you very much for a very nice and comprehensive review talk. So I have a comment on the high latitude inertial modes that you showed us in the last slide. So it seems like the direction of this polar spiral you're showing is the opposite to the observation. And I would like to mention that if you drive the mode by latitudinal shear, the mode tends to have this wrong spiral because they need to transport the angular momentum poleward. But I would like to mention that, so these modes need to be paraclinically excited. And in that case, the mode have Reynolds stress, which transports the angular momentum equatorward. But in that case, you can drive the meridional flow, which counteracts this, which cancel out this angular momentum transport. So it's just a comment, yeah.
Yeah, I do agree with you. This polar vortex has the opposite direction, and we are working so we are doing all these experiments that you are mentioning. And since we force the differential rotation, we obtain baroclinicity naturally, but we do have two free parameters that are two time scales. One for the thermal perturbations and one for the forcing of differential rotation. And we have noticed that playing with these two parameters, we can change the baroclinicity and we can change how these inertial modes looks like. So yeah, thank you for the comment.
Okay, we have last question, Rajaguru.
So I'm just curious to know what's the structure of the meridional circulation you have in your simulation? I haven't seen any.
Yeah. In global simulation, in most of them, the meridional circulation is multicellular in radius. Yeah. Okay. So there are a few simulations. Loren Matilsky with the Rayleigh code, they have some simulations with a very large difference in scales of density. And when we have a lot of density scale heights, it's possible to get a poleward differential rotation very close to the surface. But then you go deep down and still you get multiple cells.
Okay, thanks.
Gustavo, so how important is the existence of a tachocline to build up large-scale coherent toroidal fields in your simulations? Do we need it or we don't need it, the tachocline?
It's very important. So the simulations that I presented, it's hard to move this. So in this movie, so you see that the magnetic field here, I don't know how, can you play it, please? The movie is the magnetic field here develops at the tachocline. And then something weird happens, and then it changes polarity. And then something weird happens, we call this alpha, and then it changes polarity. So this happens at tachocline levels. If I don't have a very strong differential rotation, radial differential rotation at this radial level, I don't have this. So it's quite important. Thank you.
Yeah, very last question.
Okay, in these simulations, are you able to measure magnetic connection in this magnetic field lines?
No, these are too core simulation to go to the reconnection regime. Okay, thank you very much.
Okay, thank you, Gustavo. Thank you very much. Nice talk. Next speaker is Abigail Frost. Okay. Evidence for mergers in stellar multiple systems can create magnetism in massive stars.
And later. Okay, thank you, everyone. Thank you to the organisers for giving me the opportunity to present our work today. My name is Abigail Frost. I'm currently based at ESO Chile, and today I'd like to tell you about some work that I did as a postdoc at KU Leuven with all these wonderful people. And going back to kind of observations of magnetic massive stars, we think this is quite a nice case for a smoking gun of a system which has just gone through a stellar merger in a hierarchical triple system to create one magnetic star in a massive binary system. So thanks to Svetlana, I don't have to do too much introductions. I'm just going to go straight back into the information about the source. So the system is called HD 148937. Svetlana mentioned it in her talk. It's one of this group of so-called OF question mark P stars. This is a class that was defined by Warborn back in 1972, and they show a number of key spectroscopic features. For example, one of which you can see in the bottom left spectra here. One of the key markers of this class is a strong C3 and equally strong N3 lines. And this chemical peculiarity that is seen across this subset of O stars is attributed now to magnetism. This particular system, this particular OF question mark P system, has a couple of things that make it quite unique. One thing is this beautiful nebulae, which you see surrounding the system. This is very rare for O stars, main sequence O stars quite generally. A recent study by Lim in 2024 did quite a nice dynamical study of this nebulae, and they find that they think it's only around 7,500 years old, so very, very recent. The magnetic field was measured directly towards the system by Greg Wade in 2012 with a dipolar polar intensity of around 1,020 Gauss. And this isn't just a magnetic star, it's a magnetic binary system. The two stars were confirmed through interferometry in 2014 as part of the Southern Massive Stars at High Angular Resolution survey run by UGSANA. And in 2019, Greg Wade looked at the system again and using these spectra, but many more. This is just a few examples at the bottom here. He looked at data from around a decade's worth of spectroscopic monitoring and determined the system to be a spectroscopic binary as well. Unfortunately, the period of the system is thought to be quite long. We think it's around 30 years. We kind of have a lack of spectroscopic data at Periastron, and we're going to have to wait until 2040 to get that data. So, in the meantime, it's been difficult, or at least it was difficult spectroscopically, to find a clear period for the system, but they found two options, one being 18 years, one being 26 years with these spectra, with varying eccentricities as well. And that's through the fit of all those spectral data and that one kind of astrometric data point from the interferometry as well. So essentially what we did in this work is we revisited the system using multi-epoch interferometric data. So building on that first data point, we got a bunch more and then tried to see what this could tell us about the system. So we took data from two instruments called Pioneer and Gravity, which operate in the H and K band respectively, and they both instruments at the Very Large Telescope Interferometer in the Atacama Desert in Chile, which you can see in the top right there. And essentially the way that we interpret, or one of the simplest ways we can interpret interferometric observables is through doing geometrical modeling. So basically creating a model of various different shapes, such as uniform disks or point sources for stars, to tell us how many stars we have in the system, and also where they are, and what they look like. And so with these multiple data, we could confirm that the system was a binary as detected from that original first snapshot, which was also taken with the Pioneer instrument. And you can see a couple of example model images from the different epochs here with the black background. So even within this 1 year, 2016, we're able to see some of that movement of the system. The final model that we have for the system is a binary where both the stars are very, very comparable brightness. The secondary on average is around 94% the brightness of the primary. And I mentioned that we get the positions of these stars accurately with interferometry. And so essentially from this 9-year monitoring, we got a lot more of that information. And you can see all of the those points in the orbit at the bottom. And it's enabled us to get a much more accurate handle on the orbit of the system, despite not having many spectra at Periastron. And so when we combined this astrometric data with the spectral data from the Wade 2019 paper, we were able to converge on one orbit. It's very long, it's 29 years. It's eccentric at 0.77. And one important thing, which was relevant for our deeper analysis of the system, is that from this orbit, we're able to get a really nice total mass of the system, around 56 solar masses. And you can see the other parameters of the orbit in that final fit there. Okay, one other key thing that was important in this, in looking at this magnetic system was spectro-interferometric data. So the gravity instrument, which is one of the instruments we used, has a spectrometer built into it. So in addition to our standard interferometric observables, we also get very nice spectral information. The resolution is only 4,000, but when you combine this with the very high spatial resolution of kind of 4 milliarc seconds that we're getting with the interferometer, and once you combine the spectrometer with that, you're able to basically work out exactly where any emission lines that you see are coming from. And that's very important. And when I was modeling the data, I tried a bunch of different things. So you can see we have this nice, bracket gamma line that we were observing in the K-band spectrum from gravity. And when I was fitting this, I tried to see if both stars in the system were contributing to this bracket gamma emission, or whether one star was. And I can only fit the data if the bracket gamma emission is associated only with the primary star in the system. And so that's interesting because strong bracket gamma emission can be an indirect sign of stellar winds combined by magnetic field and is often used as an indicator for magnetic fields in hot stars. And so that kind of implied that, yeah, maybe only the primary star in the system is the source of that 1,000 Gauss magnetic field that we find. And this was strange because why would only one of the stars have a magnetic field and the other one not? Okay, so given these new insights from interferometry, we decided to revisit the spectra of the system to have a kind of a new analysis, given that we know something a bit strange was going on here. So we used various spectral disentangling methods to take all of the, to split the archival spectra into individual spectra for each stars. We used a grid disentangling approach to iterate over the semi-amplitudes of, to determine the semi-amplitudes for each star. And then combining that with that total mass that we got from interferometry, we were able to get individual masses for the individual stars. So we think the primary is nearly 30 solar masses. We think the secondary is a bit less massive at 26.6 solar masses. We also did SED fitting. We had nice magnitudes from the interferometric data because we had flux ratios for the stars. And we also had, we used the disentangled spectra that we derived from this step to kind of do some SED fitting as well to get the luminosities of the stars, which you can see at the bottom of this table here. And then we did atmospheric modeling of our disentangled spectra using the CMF Gen stellar atmosphere models to get further parameters of the two stars. And so you can see snippets of this here. I wanted to pick a couple of examples just to kind of show you one of the issues we ran into here. So you'll notice that, so here we have two examples of two lines that we used for the atmospheric modeling for the primary star and one for the secondary star. These are the same lines in each case. And you'll notice that here we have a very poor fit, and we think this is because of the confusion with the magnetic lines. We have another feature of the OF question mark P spectra is that we have a lot of this, a lot of effects, sorry, on the Balmer emission, and so this is why we can't get a good fit here because that is just not included in the CMF Gen grid. So we were never going to fit that with these models. But despite this, we were able to constrain the secondary very nicely, and we could get a decent fit to the primary as well. And you can see the final results of that atmospheric analysis here. We have temperatures, surface gravities, and for the secondary, where we did not have this confusion from the magnetic lines or the magnetic activity, we're also able to calculate a nitrogen enrichment for the secondary as well. Okay, so putting all of those parameters that we derived onto a HR diagram, we can see something a bit strange. So not only do we think that there's only magnetic field in the primary also looks significantly younger than its secondary companion. Here you can see some isochrones from Brott 2011 stellar models. And if we're just looking at these points here, which are the kind of the results from that atmospheric modeling, then we see we have at least a rejuvenation of a megayear for the system, which is very strange. We decided to look into this in a bit more detail by using another set of models. We used the Bonsai Stellar Evolution Model Wrapper to see if we could find solutions for these models which would agree with the parameters that we derived from our atmospheric modeling. We could, and we took two cases for the secondary, one where we included the nitrogen enrichment on the right, and one where we didn't, because we weren't able to do it for the primary, so we did both cases when we were comparing the models here. And this supported what we found. So yes, we could find model solutions for these two types of, for the two stars. And from the bonsai grid, we find that, yeah, there has to be a rejuvenation of at least 1.5 megayears if we're not considering the nitrogen enrichment. And if we do, then it's even bigger. So something appears to have happened within the system to change the primary. If we're assuming, I mean, the secondary looks quite normal. It looks like a fairly typical O star, which implies that, okay, what has happened to its primary companion to cause this difference and make it magnetic and make it look younger than the secondary companion. And so, yeah, sorry, just to clarify, in the plot I showed before, these results are shown as the contours here. And okay, so when we were thinking about what could cause the rejuvenation, I don't have time to go into all of the different mechanisms which could do it, and also Svetlana already talked about these. But we were thinking about, we decided to see if a merger could explain what we were seeing. We already knew we had this large ejector, and when we think about things like red novae and potentially, you know, other bright ejector objects, mergers can potentially help to cause this. And you know, in particular, I just read a paper by Rysiowski Hirai in 2021 where he was trying to explain Etikar through a triple merger. So it seemed like something worth investigating. And we've already seen this plot in Svetlana's talk. And essentially, we reached out to Fabian Schneider, who ran this grid of merger models for massive stars, and to see if it could fit. Again, we went to these because we know from this work that when the cores of the stars in Fabian's models merge, it becomes you get very large convective merged core in your star. It's very large, it mixes a lot of hydrogen, and that subsequent fusion that you get makes the star appear younger, so it appears rejuvenated. And also we know from his models, what he found in his models, is that, yeah, the shear between the two merging cores and the vortexes between them of the two merging stars amplifies the magnetic field as well. So we thought, okay, maybe can we find a solution from these models which matches the observations? And, sorry? Sure. And yes, essentially what we found was, so we reached out to Fabian and he looked through his models and saw if we could find something that could work, and he could. We know from the dynamical estimate of the age from this limb study that the nebula is young, so we're assuming that the merger likely just happened, and therefore we're assuming that the current mass of the primary star is the post-merger mass. And so essentially we wanted to see if the models could reproduce the age discrepancy that we see, so reproduce that rejuvenation, and we use the secondary as kind of an independent clock for measuring this. And so here we have two groups of results. Again, this is including the nitrogen enrichment and not including it. And so we can find a solution in both cases. The kind of ratio of the masses of the stars involved in the merger changes significantly between these two cases, with a more unequal mass merger for the case where we do not, where we do include the nitrogen enrichment. But essentially we conclude that mergers with an initial total mass of 35 solar masses can explain the mass of the current star we see and explain its rejuvenation with respect to its secondary companion. And if we look a bit more at the nebulae, we haven't modeled this specifically, but it does seem to be potentially quite a nice fit to this piece of the puzzle. The mass of the nebulae was, or a rough estimate of the mass of the nebulae was determined by Mayhe in 2017 to be between 1 and 12 solar masses. And from the merger models, we find that between 1.7 and 8.2 solar masses would have to be lost, and those ranges quite nicely overlap. And also the nebula is enriched as well. It's enriched in CNO process elements with particularly a lot of enrichment in nitrogen in these bipolar lobes. And so if someone can help me with playing the video maybe, then yeah, to summarize, we think that essentially HD148937 was once a triple system, and we think that two of those stars within that triple merged to form a magnetic star, and leaving the secondary is kind of like the witness to this quite explosive event. And if you'd like to see the full details, then please check out the paper. It came out in April this year. And yeah, I'm happy to take any questions. Thank you very much.
Thank you.
Questions? So I have a question. The merger can probably only amplify magnetic field, not generate, right? So what is the origin of initial magnetic field? Is it a convective core, or what generating these stars?
I don't know what's happening. Yeah, that's a good question. Unfortunately, we haven't looked backwards in our modeling to try and work out particularly the properties of the stars before the merger in great detail. But that would definitely be something to investigate. It's mostly an amplification rather than a generation, as you say. So it had to be some kind of level of fossil fuel, but particularly towards, well, but at least now we know in the system that the primary is definitely dominating, we think, the magnetic emission of the system. But looking backwards, I'm not sure because we haven't done that kind of backwards modeling yet.
Are there any simulations that show vortex formation at mergers? You said that vortices generated and then it's amplifies magnetic field.
Yeah, I mean, that was one of the point of Fabian's models, is that is a process that happens. And I think it's his 2019 and also his 2021 paper have a lot of information on that.
Thank you for your presentation. Do you see in observations any variations of magnetic field?
Sorry?
Variations of magnetic field.
Yeah. There is variability in the C3 and the N3 lines, which have been traditionally associated with this magnetism. I didn't work on it specifically within this project, but in Greg Wade's 2019 paper, he did discuss that in more detail. Particularly, there was a significant change towards the later end of his epoch of spectra in the behavior of those lines. And additionally, there's a couple of other forms of variability which have been seen. There's also a 7-day variability associated with the system, which was originally thought to be due to binarity, but now that we've resolved the stars, we know it's not, because they're on a much longer orbit than that 7-day, than just binary orbiting would cause for that 7-day variation. That's still an open question. We confirmed that period with test data. Actually, I do have a slide for that. Yeah, here, so we confirmed it with the test data that there is around a 7-day period. It doesn't quite agree with the rotational speeds that we do derive for the 2 stars in the system. So maybe it could be a misaligned axis, we're not sure, but yeah, that's still an open question for the system, for sure.
Okay, thank you very much. Next is Konstantin Getman, problem convective dynamo activity in young stars with Chandra X-ray Observatory.
Right. Hello, I'm delighted to present our talk, Probing Convective Dynamo Activity in Young Suns with the Chandra X-ray Observatory. My collaborators are Eric Feigelson and Gordon Garmire. In this talk, I will give you a few examples of how direct observations of X-rays from young stars can offer clues about the dynamos, underlying dynamos. First, introductory to young stars, also known as primi-sequence stars. They typically born in rich stellar clusters with giant molecular clouds. The fast rotators, they're powered by gravity, they're gravitationally contracting. On Hirschsprung-Russell diagram, they first evolve along Hayashi tracks, nearly vertical tracks, where they're fully convective. Then they switch to Henny tracks, where as they develop radiative cores. Many of these primi-sequence stars are surrounded by protoplanetary disks. And this is the schematic of a star with the same mass. On the left is a very young primi-sequence star that is still fully convective. On the right is already evolved star, heavily contracted, developed radiative core, like our sun. And we know that alpha omega dynamo generates magnetic fields, and it operates in Tucker line and a convective envelope. In contrast, in primi-sequence stars, convection-driven dynamo generates magnetic fields, and it operates across the entire volume. Because of this operation across the entire volume, this dynamo is much more efficient, and it produces stronger magnetic surface fluxes, stronger and larger active regions, and stronger X-rays. This is the comparison of magnetic field strengths, average magnetic field strengths between main sequence stars and primi-sequence stars. Main sequence in yellow, primi-sequence in black. And you can see that primi-sequence stars systematically have significantly stronger magnetic field strengths. Although in sports, in local sports, magnetic field strengths are similar between main sequence and prime sequence and reaching several kilogauss, but magnetic filling factors in prime sequence stars are much more higher. They exceed 80–90%, whereas in main sequence stars, this is typically less than 20%. Over the past 25 years, utilizing Chandra X-ray Observatory, which is famous for its high spatial resolution and sensitivity, we were able to observe over 50 galactic star-forming regions. These harbor hundreds of stellar clusters like this. This is an example Chandra image of Orion Nebula cluster. And to the right, we see a typical light curve, X-ray light curve of a prime sequence star. It shows two X-ray levels. One is associated with prominent large X-ray flares marked in red, and the other level is associated with quasi-continuous level. We call it characteristic X-ray level. This is a superposition of numerous weaker unresolved flares. X-rays from prime sequence stars, they typically generated in the same way as on the sun via magnetic reconnection in corona. And empirical evidence suggests that prime sequence X-ray, they adhere to this simplistic standard model of solar flares. Specifically, microwave, radio, hard X-rays, and optical emissions, they typically precede soft X-ray emission. This is part of Newport effect within this model, and Newport effect was observed in many prime sequence large flares. Also, large prime sequence flares were modeled, numerous flares were modeled, and specifically on this inferred plasma temperature, plasma density diagram. This is evolutionary diagram, and you can see the U-shaped pattern. The same pattern is present in solar flares, U-shaped patterns here. And similarity in U-shaped patterns suggests that the heating and cooling processes in prime sequence and solar flares are similar. Also, the modeling of prime sequence flares suggests that the X-ray emitting coronal loop structures are much, much higher than that on the contemporary sun. They can reach heights of few to several stellar radii, regardless of the presence or absence of the disk. On the sun, the X-ray coronal structures are typically very close to the surface, and on occasion, they can reach half solar radius. And some MHD simulations suggest that because prime sequence stars are very fast rotating, that perhaps they generate active regions of polar polarity in the polar regions due to polar updrift. And these gigantic active regions can support extremely large, strong magnetic dipolar structures that confine X-ray emitting plasma in line with our empirical evidence. This is another way of comparing prime sequence and the solar flares, and a few properties are compared, and you can see prime sequence flares that are marked in black and red that are much more stronger than solar flares that are marked in blue. Specifically, emission measure is stronger, plasma temperature is stronger, durations are longer, and scales of coronal structures are bigger. And this is energetics. This graph shows here an occurrence of flares as a function of X-ray flare energy for prime sequence stars in the upper right corner, and for G-type all stars like our sun in the bottom left corner. For the reference, the flaring energy of Carrington event is shown here. And you can see that our sun can produce typically one Carrington event per few hundred years, whereas one solar mass prime sequence star can produce 25 Carrington events per day. Ladies and gentlemen, per day. It's much more stronger, much more active. Prime sequence stars also produce these mega flares that our sun are magnetically incapable of producing. So you can see how much more active and violent was solar neighborhood, solar environment during prime sequence stage. And also such flares and associated coronal mass ejections, they play key roles in dissipating protoplanetary disks around young stars and removing atmospheres in close-in planets. Back to dynamos, we know that on main sequence, older stars, lots of main sequence stars show magnetic cyclic activity. And On primo-sequence stars, the situation is different. First of all, in the literature, there is no evidence of empirical magnetic cyclic activity. There is one theoretical work I find that they suggest perhaps for some primo-sequence stars due to a special condition might show cyclic activity. So we recently analyzed multi-epoch Chandra data of Orion Nebula cluster, and we measured this amplitude of long-term X-ray characteristic variations. Remember, characteristic level is where you remove large X-ray flares and just live with characteristic variations, measure the amplitudes, and you see that amplitudes are very small, less than 60%, suggesting either absence of intrinsic magnetic dynamo cycles in young stars or mitigation of cycles by saturated primo-sequence X-rays. By the way, the stars I'm talking about are Orion Nebula stars. They're very young with ages less than a few million years. With regards to saturation, another independent paper suggests this is X-ray luminosity is a function of age. What is shown here points at different stellar clusters. And you can see during the first few million years of evolution, X-rays are generally saturated. And indeed, it is related to saturation of magnetic stellar fields on the surfaces and to some degree to the magnetic dynamo. But later, for all the ages above 5-7 million years, both X-ray luminosity and spot area decrease with time. And this temporary decay is actually implies this relationship. X-ray luminosity is proportional to the stellar surface magnetic flux. And this relationship actually was known for the past 20 years. First appeared in Pevtsov 2003. It applies to many stars of different types, specifically to various magnetic elements on the sun, to all the active stars, and to primo-sequence stars. Pevtsov back then had only a dozen primo-sequence stars with known measurements of magnetic field strengths via Zeeman broadening. And this universal law implies perhaps the universality of magnetic flux propagation and dissipation regardless of the nature of the dynamo, whether it's alpha squared in primo-sequence, alpha omega in older stars. However, there are outliers from such law. For instance, this X-ray superflares. It seems like they deviate from this law, perhaps due to the fact that magnetic spots in spots that support these flares are much higher than typical of few kilogauss and reaching strengths of 10-20 kilogauss. But we want to place many more primo-sequence stars on this diagram, not only this dozen with known magnetic fields. We have thousands of primo-sequence stars with known X-ray luminosities. And to do so, we assume a theory of a fully convective dynamo. Specifically, these brilliant papers, they suggest that it's kinetic energy of convective flows that sets the magnetic field strengths on the surfaces of the stars. And they estimated theoretically with some empirical analysis, they produced this formula with the simplistic parameters mass, bolometric luminosity, and radius. Applying this formula to our 1,000 primo-sequence stars, we can place them on this diagram. They color-coded here is light green, red, and orange. And you can see that light green, those are the ones that still on Hertzsprung-Russell diagram, they still follow vertical Hayashi track, they're fully convective. And those Ehrlich-Hennig track stars on Hertzsprung-Russell diagram, they both follow this universal law. But it's orange stars that located on the late Hennig tracks, they strongly deviate. This is a magenta fit, and it's all strongly deviate from this universal law, suggesting that for orange stars, this formula is no longer applicable. So these orange primo-sequence stars, they no longer possess a convection-driven dynamo. And so we see indication for a transition from alpha squared to alpha omega dynamo. So this is my summary. Dynamos in young suns are much more efficient and capable of supporting more powerful flares compared to our current sun. During the first few million years of stellar evolution, convection-driven dynamos produce saturated X-rays and likely saturated surface magnetic fluxes. There is a transition takes place from convection-driven dynamo to alpha omega dynamo, and it occurs on late Hennig track stages of stellar evolution. And there is no observational evidence of strong long-term magnetic cyclic activity in very young primo-sequence stars that are still fully convective. Thank you.
Questions?
Yeah, thank you for a very nice review talk. I have 2 comments about the solar flare part. Would you please show me again, maybe page 10 or
is it modeling of solar
you,
flares?
You wrote the standard model.
Yep.
Showing the loop.
Sure.
But the loop model is not the standard. Please remember, actually, magnetic reconnection is very important. Above the loop, we have a reconnection point and the plasmoid ejection. That is more important. And so this is only a part of a standard model, not a full model. Please remember.
No, I know this. I know this. I wanted to be more specific. It's when soft X-rays take place. And soft X-rays take place in the second phase of this model.
But this is becomes more important in the page 10 or 11. You show the emission measure temperature diagram.
Yes.
Yes. Here emission measure temperature. You show the separately premium sequence flares and solar flares.
That's correct.
But actually, that is not good. And if we consider reconnection physics, then both can be understood in a unified way. And that was proposed by myself, Shibata, and Yokoyama in 1999, and also 2002. And Ashbanden's paper actually not good. And he himself understood his result is not good. And later he wrote again, revised version of the paper, citing our Shibata and Yokoyama can be fit with real solar data. So later I'll show you my all the papers.
Where do you propose the locus of solar flares should lie on this diagram, emission measure versus temperature?
You see, in this diagram, Ashbande wrote several different lines which do not connect stellar flares and solar flares. But actually, if we consider the physics of reconnection correctly, both can be connected in a single line.
Thank you. I can point here with regards to, well, first of all, you see that primisequence flares, they lie on active region locus. So you suggest to move solar flares up a little bit, the locus of solar flares
the point
up.
is the physics of the flares can be understood in the same physics. That is most important.
And that was also my message that most of the solar flares, they show similar properties as primisequence flares show similar properties as solar flares, but on much larger scale. Everything is just much stronger, much more powerful, much more longer. Thank you.
Okay. Question? Yeah. Can you please repeat what is the evidence of a change between the fully convective alpha square dynamo to the alpha omega dynamo?
The evidence as these stars that are located on the late Henny Tracon Hirschsprung-Russell diagram, they already developed quite large radiative cores. And when we just apply this formula to estimate theoretical magnetic flux, assuming the formula is applied within the framework of fully convective, convection-driven dynamo, this theoretical magnetic flux completely fails from this locus of universal law that we expect for all stars to be applicable to. And the failure is because this formula is no longer applicable to this late Henny track stars. And because convection-driven dynamo doesn't work any longer. What other can it be? Alpha omega probably, because radiative core isn't there.
Okay, thank you, Tim, for very important results. Thank you. Okay, we have last, also very important talk by Amy Norton about nests of magnetic activity.
I think the next plenary talk is at 5:15, right? So we have time to do this without missing. Okay, I know we're running late and I'm the only thing between you and your beer, which is dangerous sometimes. So I'll try to be quick. This is a movie, if we could go ahead and play it. I'll be talking about activity nests. There are regions where there's repeated flux emergence. I'm not going to use the term active longitudes, because in stellar communities, usually that means there's 2 active regions in North and South Hemisphere, but instead I'll be using the term nest. Does the movie not play? Do I have to do something? Oh, but nothing's playing. Oh, okay, let's see. The green one. The big green one. Okay, all right. Yeah, I got it. I got it. Sorry. And then to advance, I use this one. Okay, thank you. So this is a active nest in May 2024. So this is for solar cycle 25. I'm going to be talking about the nests that we're finding in solar cycle 24, but this is the famous one that was so large that created so many auroras. So I just thought I'd show a cool movie of it. This is actually part of a nest. It had counterparts in February as well as in June. So it lasted roughly 6 months. So let's see if this works here. Oh, I'm working with, I had a summer student, Alex Mendez, and Ruji Chen helped a few years ago. And now I'm working with the coffee collaborators, Nick Featherstone, Lisa Upton, Lauren Matilsky, Andre Munoz Jaramilla, and Vibhuti Jha. This again? Wait, somebody help me. Is it this arrow here? Oh, it's only this, so I don't use this one at all. Okay. So the definition of active nests, the idea has been around for 50 years. Castanelli definition was that there are 3 or more active regions emerge within 15 degrees longitude and 10 degrees latitude of each other. This occurs over a minimum period of at least 4 months. I'm showing you just a very simple Carrington rotation map data. So the time, these are Carrington, oh dear, where's the laser pointer? This one. Oh, okay. I'm so sorry. Okay, so this is time moving in this direction, and this is longitude. And just remember that in Carrington rotation format, time moves from right to left here. And so this is just one example of an activity nest. So it's generally thought that when a solar cycle starts, you have just 1 nest, and when it ends, you roughly have 1 nest or 0 nests or maybe 2. And then in the middle of the cycle, you have 4 to 6 nests that are spanning all the longitudes. This is some of the results. This is what I'm showing you here is 2 maps, one for the Northern Hemisphere and one for the Southern Hemisphere. Each point in here is an active region with a NOAA number. The symbol size is proportional to the flux. There's returning active regions are not included, so we get rid of them if they are returning, and so we're only including new flux. The differential rotation rate isn't accounted for, it's only the Carrington rotation rate, and the slopes indicate whether it's retrograde or prograde, the active regions. So, if you see something like this, then it's prograde, and if you see something that's slanted the other way, like this one, it's retrograde. So you can see when the cycle begins, especially in the Southern Hemisphere, you just have 1 nest. You can see in the solar cycle maximum period, you have multiple M=4, M=6 nests. But I don't really like this result, and I was convinced that we shouldn't publish it because basically I'm finding, the results I'm finding are just the definition that we're searching for. So, we needed to have 4 Carrington rotations, and the average lifetime is 4.4, 4.3. We needed to have 3 active regions. I mean, we're basically just finding what we looked for. And so that felt like it was a problem. We needed to search, the parameter space needed to be bigger. We needed to search to look for more like higher retrograde, prograde, and longer gaps between active regions as a nest. So this is the data. I'm just showing it to you. I'm not going to say too much about it. These are stacked Carrington rotations. So basically each one of these is a month. Time runs from right to left here. And then you can see the years stacking up in this direction. And this is the beginning of solar cycle 25. Your eye automatically sees the activity nests when you look at this, but sometimes your eyes are deceiving you because you're getting returning flux. So like from here, there's no new flux in this one. That's just the returning active region as it's decaying. So you need to be careful interpreting this if you want to remove the decaying active regions and only look at new flux. This is the southern hemisphere. We analyze them separately because we believe that the cycle is progressing differently in the northern and southern hemispheres. Again, you can see the solar cycle 25 beginning, and you can just identify by eye the nests, and you can see that there's only a couple at the beginning of the solar cycle. There's many in the middle, and then none at the end. And I found this kind of odd. Usually you just start with one nest, but in solar cycle 25 in the southern hemisphere, you already have 3 or 4 nests early on. So what are the causes of nests? They could be large scale convection, such as giant cells. This is a paper by Weber, Fan, and Misch. If you have any questions, Mark can explain it to you. And in this, I believe it's the ASH code, and they are simulating convection, but also having thin flux tubes rise. And these little black asterisks that you see here, maybe you can make them out, are where the flux tubes are rising as they're interacting with the giant cells, the giant convective cells. So it's thought that giant convection cells could be guiding the thin flux tubes as they rise so that you get more alignment in their emergence in time. You can see here that the downflow lanes, which are the purple or dark blue, are moving in this direction. So this is actually a prograde motion in time. And you can just see where the active regions are there, or where they would be in this model. Another cause of nests is the possibility of instabilities acting on the tachocline. So you have plenty of theory and work done that shows that there's global hydrodynamic and magnetohydrodynamic instabilities that are hosted on the tachocline, and you could get this tipping and warping of the toroid of the field. Like you see here, you can see the warping, and this is another way to show that, where the red is bulging material in the tachocline, and the red is depressions. This is from Dick Potty, and this is from McGray. And where there's bulges in the toroidal, where the toroidal band lies, you can get repeated emergences. And again, we get to see this plot. It's successful when everyone's showing it. But another cause of the nest, there's been a lot of work done on inertial modes in the sun in the last decade or so. And it's possible that the locations of the nests and their rotation rate are related to these inertial modes. And in this plot, this is the equatorial rotation rate from the depth of 1 to 0.95 radius. And this is a 27-day rotation period. And this is the high latitude inertial mode. So I don't think they're probably going to be guiding the active regions. The orange dots or symbols are the critical latitudes, and the equatorial Rossby modes are shaded in black and gray here. And so this is the ones that might actually be guiding where the active regions emerge. And so we want to use things like this and results from models to guide what frequency bands we look at for the activity nests. Also, there's a lot of interest in activity nesting behavior on other stars because you see highly variable intensity and chromospheric activity variations in stars, sun-like stars, and there's not really a way to explain that. Well, we don't really know why it's happening. One way to explain it is if the star is hosting very strong nesting behavior. And so in this plot over here, you can see the strong variability of the radiative flux in a star nicely known as this number. And then below it, you can see the sun, and we needed this much active region activity in order to get this dip to somehow match. It's close in amplitude to some of these. This is a plot. We're getting so much more data from stellar observations now with so many good spacecrafts or missions that are dedicated to studying other stars. And this is one such star that actually has a 3-day rotation period, and you can see the active region and facula darkening associated with that. There's also a very famous phenomena with nesting that's called the flip-flop phenomena, and there's been a lot of work done on this. I'm showing a plot from Bergagina and Usoskin from 2003, and the idea, this is a little bit different than what you've seen before. This is time on this axis instead of the y-axis, and this is the phase, just meaning in longitude how the nests are progressing. And so the idea is that you have 2 nests on either side, like one at 0 degrees and one at 180 degrees in longitude, and that the dominance of the nest flip-flops back and forth. So one nest might dominate and be more active for 6 months or 3 years, and then it flops to the other side. I just want to say that there is a lot of filtering that goes on to get this result, and I have not yet done this, or we have not yet done this with the cycle 24 data, because it feels like we're discarding too much information. Too many active regions would not fit into this behavior. You know, these are 6-month, each dot is a 6-month average, and they fit a light curve to where the sunspot is that's unnaturally strong in order to recover these phases. I don't believe it's a mass hallucination, this phenomena, but I do think it is not including all the active regions in their behavior. So we've looked at some wavelet analysis for the cycle 24 data, and this is one result. So what you can see here is the years running along this axis, and this is log period, and I've typed in the periods over here so you get a sense for how many days the active regions or where the power is and how many days. And so I flipped the southern hemisphere just so it feels a little bit more natural to look at it for the sun. So you're thinking the sunspots are close to the equator, but anyway, and you can compare the amplitudes a little bit better. So this is basically Carrington rotation data summed over all longitudes. So you just have a time series, a single time series. You have the magnetic field, absolute value of the magnetic field versus time, and you look at the wavelet power. And so one thing you can see here is there's very significant hemispheric asymmetry. It goes from some power in the northern hemisphere to the southern, to the northern, to the southern, back to the northern. And to be quite honest, because the signal in magnetic field time series is basically just a single peak that may last 1 or 2 days and not a sine curve over the entire longitude, I don't fully understand the beat frequencies that may be existing on this, and I need to spend more time on it. I don't know, maybe I need a different mother wavelet or something for this analysis, but it's very powerful. We can look at year by year, different frequencies. We can choose to isolate the frequency range we look at by choosing the different scales of the mother wavelet and things like that. So just for an example, this is a normalized power as a function of the period in log 10 days. And these are 4 years of the solar cycle for the northern hemisphere. And you can just see, you can identify different peaks in here that roughly correspond to the change in latitude, but not exactly. So in 2011, you have a 31-point-something day power in the red curve here, and you can see that the periodicity reduces as the active regions go down in latitude closer to the equator. But you also get this peak at 14 days, which is telling you that you either have a flip-flop phenomena where you're seeing the rotation period. Oh, okay, I'm actually taking more time than I thought. Okay, conclusions. I don't have definitive results right now. In order to fully capture the nesting behavior, I think we need to search a very large parameter space. My guess is that there's more than one behavior that's more than one mechanism that is causing active regions to nest, and they have very different rotation periods and look different in the data. So for example, we can use the wavelet analysis for a given year, given latitude, to hone in on the rotation periods that are there, and then go back to the data and analyze it more with Python codes, looking for, using logic gate type analysis to identify what's happening. And one thing I wanted to mention is that while plenty of these active regions are looking like there's a prograde motion here, there is some indication that nesting is occurring in a large scale pattern that we're not finding because we require 3 active regions over 4 months, but is occurring at a very retrograde motion that you can see here, which may actually end up being this flip-flop behavior that they reported. But basically, we're working on this with coffees, and it's an interesting topic, and you'll expect to hear more from me in the future. Thank you.
Okay, we have time for one question. Yeah.
Yeah, Dibyendu, this is an interesting line of work. Now, I am interested to find out if the active nets appear uniformly in latitude or they appear tilted across latitudes, reminiscent of a toroidal field which is sort of banded and tilted, which would happen if the toroidal field is being sheared by the differential rotation. Toroidal field would get kind of
How big of it?
tilted.
How big? How large?
It would be very large scale. I mean, one would expect it to go across tens of latitudes.
Well, we can search for that. Right now, the way we're searching is that it has to be within 10 degrees of latitude of each other. Not obviously in the wavelet analysis, but in the other analysis, we limit what we're searching for. But this is another reason why we want to expand the parameter space and search all possibilities.
Okay, thanks, Amy. Thanks, everybody here. So when you prepare your talks for tomorrow, please remember that your allocation time includes questions. Okay, so then we don't finish late. Okay, so tomorrow at 10 o'clock, poster session. We start with poster session tomorrow. Thank you.